relevant for both of the teams. So welcome to this afternoon session that will follow into tomorrow morning. So starting us off is Sean Honemichael with a comparison between two different types of chemistry mechanisms, TS1 or T1S and TS4. Oh. Great.
Ready?
Yeah, go ahead.
Okay. So for anybody that doesn't know me, my name is Sean. I'm a co-CamChem liaison in ACOM with Rebecca, and so I work closely with both Simone and Rebecca, and I'm just gonna give a talk of comparing the Mozart T1S and Mozart T4S chemical mechanisms. I'll kind of go over a few key species and look at some of the costs and budgets and some of the differences between a few different species. And so yeah. So the two chemical mechanisms that I'm comparing are T1S and T4S. T4S is basically a simplified version of T1S with less reactions, a few less species included. And so the expectation is with that simplification, we expect a lower cost and a faster running simulation. And ideally, we also want the chemistry, the budgets, the biases to be very similar to what we would see with T1S. So that's what I'm gonna go over here. So we'll start with what I'm doing. So we have three different model runs that we'll be looking at. One is uses the T1S mechanism, and we have two that use the T4S mechanism. Our second T4 run that I call T4SR2 uses a different CSM tag. The T1S and first T4S run use the CESM3 beta 02 tag, and then we have one that uses the CESM3 beta 04 tag, which has an updated dust tuning. And our overall model setup is there on the left, free running model, NE30 mid-top, 93 vertical levels. We're using CAM7 physics, MAM5 aerosols, and our run goes from total run length was 1980 to 2015, although the comparisons are only covering 1995 to 2011, so that it aligns with some of our observations that we have that we're comparing with. And so timing, cost, and stability. The T1S run comes in at around 2.75 sim years per day. Our T4S run comes in at around 3.9 simulated years per day. That gives us almost our T4S runs about 1.4 times faster. Excuse me. And our second T4S run is pretty much the same as our first one. As far as stability goes, no stability issues with the T1S. In the first T4S that ran on the beta 02 tag, I did have to adjust the time step several times throughout the run to get past a few spots. Although with the second one with the updated, the beta 04 tag, I didn't have that problem, and it seemed like it was stable. So that's good. And so now look into some of the species that we're comparing. The first one is ozone. So what we have here is on the left is a comparison of our T4S and T1S and the with differences and percent change. And overall, they look pretty similar. We do see a little bit of a difference in the Southern Hemisphere UTLS region. That's about a 10% difference. And you see that on the right, these are 200 hectopascal polar plots. The top two panels are Northern Hemisphere with T4S on the left and T1S on the right, and the bottom is the Southern Hemisphere. And you can see in the 200 hectopascal plots, you see that difference a little bit. So that is one thing that we see that is a little bit different, but the Northern Hemisphere does look very similar. And hopefully you'll be able to see this. These are Taylor diagrams comparing our ozone from the models with ozone sondes. And this is kind of why I'm only looking at 1995 to 2011 because that's what our ozone sondes cover. Given that it's a little hard to see, you can imagine that from top to bottom, the altitude is increasing in these panels, and from left to right, the latitude increases. So the top left, you're looking at the low level tropics, and bottom right, you're up into high latitude upper levels. And the red dots are our T4S run, the blue dots are our T1S run. And kind of the key takeaways from the series of panels is compared to ozone sondes, kind of have the lowest correlation in the low level tropics, where I have it marked with a purple box and a 2. And we get the best correlations in the mid to high latitude stratosphere, marked with the green box, and a 3 kind of in the lower bottom right. The placements are pretty similar between the two model runs, which is good to see. And if you look real close, you could see kind of some of the differences that we saw in the last plot with the Southern Hemisphere UTLS and the boxes that I had marked 5, although it's not too far off from one another. Another way we can compare these is with the seasonal cycle. So on the left 4 panels are Northern Hemisphere polar region. The right-hand 4 panels are the Southern Hemisphere polar region. And we're just kind of looking to see where the differences are between the two runs and how they the biases look. The dots with the black lines going up and down, that's the mean of the ozone sondes and the min and max. And so what we find is in the Northern Hemisphere, 50 hectopascal in the early part of the year, there's a little bit of a deviation between the two models. And in the green box at 250 hectopascals in the Northern Hemisphere polar, in the early to kind of the first half of the year, you see a little bit of difference. And then the Southern Hemisphere at 50 hectopascals, and then the orange box on the top right panel, you can see that there are the difference that we saw in the Southern Hemisphere UTLS kind of appears to be a little bit more of a Southern Hemisphere summer issue. We see it mostly in like from December through, I don't know, like March or April. So that's ozone. So now we'll look at briefly at carbon monoxide. The left-hand series of 4 panels, similar to what the panels that we saw with ozone. Top being our T4S run, the T1S run, and then we've got the difference between the two and the percent change. And then on the right, just a map plot at 850, so near the surface, and can happily say that we don't really see any significant differences at all with CO, which is good. And just looking at our bias, this is our model minus Moppet observations, and we really the top left is our T4S run. The bottom right is the our T1S run, and we don't really see too much of a difference between the two, but we do. So, you know, we share the same low bias that we between the two. And another thing that we're looking at is the tape recorder. So on the left-hand side, we're comparing MLS ERA 5 to our 2 runs, our 2 beta 02 runs, T4S and T1S. And I think Simone showed this on Monday, but we don't see any major differences between the 2 runs, and they overall look not too bad compared to MLS. And next we look at aerosol optical depth, AOD, and this is compared with MODIS between our 2 models. Our beta 0 CSM3 beta 02 models runs. Overall, the top 2 panels, you don't see a huge difference between the 2. We have the same kind of low bias in the northern hemisphere, and this a very similar high bias in the southern hemisphere. And so now we switch a little bit and look more at our T4S R2 run. So this is one, as a reminder, this one used the beta 04 tag, which has the updated dust tuning. And so what we see is, generally speaking, a little bit more dust in the northern hemisphere around 20 latitude and less elsewhere. I kind of annotated there, we're at 20 north, that's primarily Africa and dust, and then negative 20 south is a lot of Australian dust. And this is just a map plot at 850 hectopascals, and this just shows that we get a little bit more the African dust, a little less Australian dust. And when you look at the percent change, the low to mid latitudes kind of, or I don't know, in the vicinity of about 20% higher. There's kind of this band of orange that you see in the bottom left-hand plot. And elsewhere we're in the negative, which means we're lower. And here's a look at the AOD compared to MODIS for our second T4S run. when you compare this, we get a little bit more of a low bias in the northern hemisphere, and in the southern hemisphere, our high bias is reduced. Places like Australia are a little closer to zero than they were compared to our T1S run. But we do see some other places, you know, like I said, things in the northern hemisphere are generally a little bit lower. So this is comparing a few species to aircraft data from ATOM. And these were some plots that Simone created.
Yeah.
And this just kind of shows that the extinction is reasonable, and there's some underestimation over the Pacific mid to high latitudes and an underestimation of organic aerosol. And then here's dust and sea salt, and this shows that our in the beta 04 tag, dust is improved, but we're still a bit high compared to observations, and the sea salt is reasonable. And lastly, this is just a table of some of the budgets for some of the different things that we looked at with for a few species, ozone, CO, some of the aerosols. Overall, things aren't too different between T1S and T4S and our second T4S run. I highlighted some of the bigger differences in red. In our T4S run, we do see our SOA burden is down by about 26%. And we have an increase by almost 9% of POM and then a negative 10 reduction in 10% of black carbon. And then, of course, with our T4S, which has the updated dust, our emissions are down by 16%. And our SOA burden is also down by 62%, which I'm not sure why, but those are kind of the biggest budget differences. And so just the takeaways overall, I think the T1S and T4S mechanisms compare well. I think T4S is doing its job. It's for the most part gets very similar chemistry, and we also get the benefit of being able to run faster and more cheaply than the T1S run. We're sharing most of the same biases, and we did see there's a few differences we saw the 10% ozone difference in the southern hemisphere and the SOA burden. But on our second T4S run, we did see more African dust, less Australian dust. The OD looked a little bit better with respect to Australia, and that did result in a little bit of a bias shift. But overall, though, things seem like they look really good. And that's all I have.
Time for one question.
So these were all nudged runs, right?
Was running.
Free running.
Free running.
Fixed SST.
Yep.
Fixed SST.
Okay.
So I can't help to compare with my T1MA and T4MA run. So in your simulation, you find T4S has higher ozone than T1, like 10%?
Just in the one area in the southern hemisphere. Otherwise, it's very similar.
Yeah, it's very interesting because in my T1MA, T4MA run, I find opposite.
Oh, really?
I find that T4 has slightly less ozone than T1, but it's very small, like 2%. I wonder if you look at NOI differences near that region.
If we looked at which differences?
I know why.
NOI.
Yeah, we haven't looked at it, but we could and see.
Yeah. because I just verified Louisa, T1MA and T1MA and T1S has the same chemistry in troposphere and stratosphere. So I would assume in the troposphere stratosphere will look very similar.
Mhm.
And another thing is I compared the cost. And as you using Chem7, so it's SE grade.
Yep.
So your cost is a little bit more than double my cost. I'm running 70 level Wacom, and you're running 93 level Chem.
Yeah.
So the vertical level isn't, it's less than double. So it's only 23 levels more, but yours is more than double more expensive. I'm just thinking maybe it's just SE, it's more expensive.
Yeah, probably.
Or any improvement in the physics.
It's also Chem7.
Yeah,
And
yeah,
this one
any
is
improvement in the Chem7 compared to Chem6 also.
Are you running notes?
Yes.
So he's not, he's interacting.
Yeah.
Free running is more because it's interactive. Okay,
Yes.
okay, yeah,
Yes.
Structure element versus fine and volume, right?
Yeah.
yes,
That's
line
the
file
difference.
volume, yes.
So we have to move on.
Okay, yeah, let's move on. Maybe you can talk more about it afterward. Our second speaker of this session is going to talk about biogenic secondary organic aerosols and Yangqi.
Should I share it here?
Yes, please. Yes.
Is the microphone here?
I think the microphone of these squares here.
Maybe.
Oh, yeah, maybe come up the front.
Maybe.
The microphone of the podium. Good afternoon. My name is Yang Shi. I'm a postdoc working with Colette Field at MIT. And today I'll talk about our work studying the chemical formation mechanism of biogenic secondary organic aerosols. I'd like to acknowledge our collaborator, Jessie Crow, also from MIT, and this work is supported by the DOE ASR program. A little bit background here. Organic aerosol is a major component of the atmospheric fine particles. This is a figure from Zhang et al. 2007. They estimated the aerosol composition in the northern hemisphere using field measurements. So the pie charts are showing the aerosol species, and their color-coded organics are in green color here. And they found that organic contribute to 18 to 70% of the total aerosol mass in the, fine aerosol mass in the northern hemisphere at these stations. And this gives an average of 45%, so almost half of the aerosol mass. They have also found that most of, or a large portion of the organics are secondarily formed. And for secondary organic aerosols, it means that these aerosols are not directly emitted into the atmosphere as particles. Instead, they are formed through the oxidation of volatile organic compounds or VOCs. And these VOCs, the secondary organic aerosol, for a large portion of them, are from biogenic sources. So vegetation like trees and grasses, they will emit biogenic VOCs into the atmosphere, and these VOCs get oxidized to form SOA precursor gases, or SOAG here. These precursor gases usually have relatively low volatility, so they can condense on pre-existing organic aerosols to form SOA. These biogenic SOA are usually considered as natural aerosols, so they can largely impact the aerosol state in pre-industrial, which is very important in shaping the aerosol indirect forcing. But they are actually one of the least understood aerosol species because of the complexity in its chemical formation. And in this work, I'm focusing on, okay, you can't see my pointer, but we're focusing on the gas phase oxidation. And Specifically, we will exclusively look at the VOC oxidation by the hydroxy radical, or OH. Reacting with OH, biogenic VOC will form peroxy radicals, or RO2s. These RO2s can react with HO2 under low NOx condition, with NO under high NOx condition, and recently people found that they can react with all the RO2s, and they can also isomerize. Here I'm only showing the reactions that can potentially form SOA, and the first three of them are bimolecular reaction. Isomerization is unimolecular reaction. In the global models, including CSM2, these reactions are not completely represented. Usually, like CSM2, it ignores the RO2-RO2 reaction and isomerization, but all of them are actually quite important because they have different reaction rates and SOA yields. So how much RO2 undergo each pathway, or the fate of RO2, actually determines the ultimate amount of SOA in the atmosphere. So in this work, we are trying to answer two science questions. The first one is about RO2 fate, how much RO2 undergo each pathway. And the second is how much SOA is formed through each pathway. So we're using the CSM 2.2. The Megan scheme in CLM5 prognostically calculates the emissions for three types of biogenic VOCs, the isoprene, monoterpene, and cisquiterpenes. And in Chem 610, we're using the Mozart TS2 chemistry with the VBS SOA formation mechanism, and also the MEM4 aerosol model. So before conducting experiments, we first try to have a more complete understanding, or a complete representation of the RO2 chemistry in VBS. So we added a few new chemical reactions. And again, all the reactions you are seeing here and all the results you're seeing on the later slides are about OH oxidation. No other oxidation are considered. So starting from the isoprene and monoterpene RO2s, their reactions with HO2 and NO are already included in the baseline Chem 6. And we included three other types of RO2 reactions on top of that. The first one, we called it others. These are the reactions that are included in the Mozart, but not in VBS. This includes the isomerization of isoprene RO2, and also the RO2 reaction with acetoperoxy and methylperoxy radicals. So these reactions actually do not form any SOA. We just include them here to be consistent with Mozart. And then we include the RO2-RO2 chemistry for monoterpene RO2s. We assume that these reactions will form 4% of SOA precursor gases at the lowest volatility bin. And the fraction here is very uncertain. Another uncertainty comes from the RO2-RO2 reaction rates. So here in this table, I'm showing the reaction rate coefficient measured by different lab experiments for a few types of RO2-RO2 reactions. We classify them as the fast and slow combination, and you can see here that for the same set of reaction, different lab measurements, their results can span by up to 2 orders of magnitude. And to address this uncertainty, I will test both the fast and slow combination in our experiments. And finally, we include the isomerization of monoterpene RO2s. We assume they form 50% of SOAG0, and the reaction rates are shown there. It is noted that this rate is actually much more faster than the bimolecular reactions. So isomerization tends to form a lot of SOA very fast, but not all of the RO2s can isomerize. Here we assume only 22% of the monoterpene RO2 can undergo isomerization. And this is another very important uncertainty. We also treated the cisquiterpene RO2s, but we don't know too much about it, so we assume it is just the same as the monoterpene RO2s. And except these chemical reactions, we did a little bit modification on the photolysis. We have turned off the photolysis of the biogenic SOA in the lowest volatility bin to mimic the photorecalcitrant fraction that is observed by these lab experiments. And finally, because we want to examine the contribution from each reaction, so we tag individual reactions separately by adding new tracers to each of them. So to examine our modifications here, we did 3 experiments. Base means baseline chemistry, plus our modification on the photolysis. And the 2 new experiments use our newly developed chemistry. Fast and slow here means we use the fast and slow combination for the R2 reaction rates. All of these 3 experiments use the present day condition. That means climate, CO2 concentration, and anthropogenic emissions are all in present day. So for some results here, here I'm showing some bar plots, the RO2 fate on the left and the contribution from each reaction to SOA burden on the right. Different reactions are shown by different colors, and I'm only showing the results for monoterpene RO2s because most of our modifications are done to monoterpenes. So looking at the left figure, you can see how much the bar plots has changed. So this means that the chemistry has changed significantly from the base experiment to the new experiments. And another thing is that if we look at the 2 new experiments, first, isomerization that is marked by the orange triangles on this plot, it contributes about 20% to the RO2 fate. This is actually quite significant because in our assumption, only 22% of the monoterpene RO2 can isomerize. So isomerization is nearly saturated in this branch. This is because the reaction rate is much faster than the other reactions. And if we look at its contribution to SOA burden, it contributes about 40%, so quite significant to the total monoterpene SOA. And for the RO2 chemistry, depending on how fast we pick the reaction rate coefficients are, it contributes about 15 to 40% to the RO2 fate, but their contribution to the SOA burden is quite minor, shown by the blue circles here. And the chemistry change results in a decrease in total monoterpene SOA burden that are shown by the green bars there. We don't think it's very significant considering how much the chemistry has changed. And this decrease in monoterpene SOA compensate with an increase in monoterpene SOA compensate with the decrease in isoprene SOA, and the total SOA burden doesn't change much. And we have to mention that all these results are based on our assumptions or choices on the reaction rates, branching ratio, and SOA yields. They are all quite uncertain, so we think more lab experiments will be quite necessary to help us reduce uncertainties in these SOA-related parameters. And then we want to know how much does the SOA formation mechanism change from the past to the future. So we did 2 more experiments using the pre-industrial and the future conditions. Future here, I'm using the SSP 585 scenario. We see that from the past to the future, the temperature and CO2 concentration both increase, and this caused the biogenic VOC emission to increase, and the NO emission peak in present day. Again, let's look at the RO2 fate and contribution to SOA burden here. This is the similar plots, but just showing different time periods. So first, still for isomerization, on the RO2 fate plot on the left-hand side, we see that the isomerization contribute quite consistently, about 20% to the total RO2 fate. That means it keeps saturated from the pre-industrial to the future, and also its contribution to the total SOA is quite significant, as shown on the right. And also at the present day, we notice that the RO2 plus NO pathway shown by the purple square there, they contribute much more in present day comparing with pre-industrial and future. This is because there's more NO emissions in present day. And if we look at the total SOA change, we see a decrease from pre-industrial to present day. This is probably because more RO2 react with NO in present day, and this pathway tends to form SOA at high volatility, SOA precursor gases at high volatility that do not favor in SOA formation. And from present day to the future, we see a sharp increase in SOA burden. This is probably because biogenic VOC emission increase, and mainly due to monoterpene emissions. And then just to show you some global distribution, here I'm showing the monoterpene plus OH SOA distribution change from the past to the future. On the left-hand side, from pre-industrial to the present day, we see increase over monoterpene source regions and decrease over relatively remote regions. That's probably where the NO emission play a role. And from present day to the future on the right, we see increase all over the globe. This is because the monoterpene increase is too significant in the future comparing with present. And next, just to summarize, in this work, we have expanded the RO2 chemical mechanism for in the VBS scheme of Chem6Chem. Basically, we include the isomerization and RO2 pathway for monoterpene RO2s. And we found that the isomerization is quite important. It's actually its own branch, and it contributes quite significantly to the monoterpene SOA burden from the past to the future at all the 3 time periods. And the RO2 pathway contribute at least moderately to the RO2 fate, but based on our assumptions, they do not contribute a lot to the SOA burden. And again, I want to emphasize that all these results are based on some very uncertain SOA-related parameters, and more lab work will be necessary to better constrain them and then constrain the SOA fields in global models. Yeah, that's all I have.
You have time for a question?
So in your mechanism, you said you had photolysis of SOAs, right?
We turn off photolysis of SOA. The photolysis of SOA is already there, included in the default chemistry.
Okay.
We turn off only, there are 5 SOA being, we turn off the first one.
Okay. All right.
What do you mean?
So, we have,
G0.
Hmm?
The SOAG.
Oh, just for the SOAGO, you turn off the
Yes.
photolysis?
Yes.
The others you keep
yeah, the others I keep.
because you don't think they are foot tolerant.
This is actually what we have to do. It's not quite accurate. This is because experiments found that there's like a fraction of the SOA that do not photolyze.
Yeah.
And we want to kind of mimic this. So the model actually think all the SOA photolyze at a constant rate, and we think that's probably an overestimation of the photolysis.
Yeah, that's what others have been finding out in the model, is that in order to get the amount that gets up in the upper troposphere, you can't photolyze a fraction of the SOA as NO2 or however it's done in the model.
Oh, yeah.
So you have to have some sort of aged photolysis on.
Yeah.
So is SOA is 0 then? I mean, is there a physical reason to use SOA is 0 because it's
Not quite physical
Okay.
reason.
No, just wondering.
Yeah.
Yeah, definitely interesting to fix that in the model. We need to think of a way to do that. That's nice.
Another question?
Yes, Louisa.
You showed the burden of SOA from isoprene and from monoterpenes and sesquiterpenes, and it was like half and half from isoprene and terpenes,
Yeah.
and sesquiterpenes is really tiny. Is that what you'd expect? I've kind of thought there'd be more from sesquiterpenes, and isoprene wouldn't be as important a core.
Do you think there's more from sesquiterpene and isoprene?
Oh, maybe not more than isoprene, but significant. I thought that would be a more significant fraction, but is that not the case? Not
So for baseline, we didn't do any modifications.
right, but it's based from other. Yeah, I don't know.
Yeah, that's probably. But one thing is that we only consider the OH oxidation here. I know that the ozonolysis contribute a lot as well to the to the SOA burden, but we didn't separate the ozone analysis SOA. So that's probably one of the reasons for that.
Oh, okay, all right, thanks.
Okay, thanks. Let's move on. Our next speaker is remote, Jindan Zhu.
Yes, I'm here.
And Jindan will be talking about biogenic emissions,
Thank you, Space.
modulating the tropospheric hydroxyl radical.
Open.
Great. Are you seeing the right screen?
Yes, we can see your slides.
Great. Okay. Hi, everyone. I'm Qingdan Zhu. I'm right now a postdoc working with Arlene Fury at MIT. And today I will present our work on developing a new idealized chemistry climate model to investigate the OH response to the climate warming. So we know that the methane is a potent greenhouse gas that contributes to the climate warming, and the methane concentration is governed by this balance between the sources as well as the sinks. Compared to the various methane sources, a sink is predominantly attributed to this reaction with hydroxyl radical or OH. In our project, we are particularly interested in how warming itself could feed back onto methane. And throughout this methane budget, there are two components that are most sensitive to the climate. The first one will be these methane natural emissions, such as wetland emission. And the second one, also the focus of our project, is this OH chemistry. So we know that the OH is determined by these highly dimensional and nonlinear chemistry climate systems, and it involves the chemical drivers such as NOx, CO, and VOCs, and these chemical drivers are determined by the anthropogenic and natural emissions. And it also involves some meteorological drivers such as temperature, water vapor, and so, and these are determined by either climate physics or the dynamics. So if we ever want to categorize the OH response to the climate warming, we find that it can come from a variety of different OH drivers. If we summarize them into two groups, the first pathway would be through these meteorological changes, and we call it as a direct OH response to the climate warming. But we also see a second indirect pathway that is through these temperature-sensitive natural emissions. So here we only focus on one of these natural emissions, which is about biogenic volatile organic compounds or BVOC emissions. Therefore, in our project, we are aiming to gain this process level constraint of how OH responds to the climate warming and identify what are the contributors or contributions of the individual process and what are the dominant drivers that are leading to this OH response to the warming. Sorting out this question is actually not easy in the fully coupled chemistry climate model because this coupling between high dimensional climate dynamics as well as emissions makes the OH interpretation quite challenging. So here I'm using ChemCam, the atmospheric only model with chemistry in the CSM2 Earth System model framework. And what I'm showing here is the model simulated annual tropospheric OH columns from ChemCam, which presents these distinct spatial patterns. And in ChemCam, our simulation, the simulation of the tropospheric chemistry is using this MODAR T1 mechanism, which consists of about 151 species and 287 reactions. And ChemCam is also constrained by overall 103 emission inputs in total for all different species and sources. And here, as an example, I'm showing the map of the anthropogenic NO emissions. And also, ChemCam prescribes these sea surface temperature patterns. And in my simulation, this SST is fixed as the year 2000 condition to drive the model's climate dynamics. So as you can tell from this schematic, the simulated OH is shaped by these nonlinear systems controlled by emissions, chemistry, and climate dynamics. So it's very hard to isolate the impact of the individual emissions or the different climate dynamic patterns and investigate their impacts onto the OH chemistry. Therefore, in my project to address this question, I built a step in the model hierarchy to study this chemistry climate interaction.
And if I lay out the current models within the CESM2 framework with the complexity of the dynamics in the x-axis and complexity in the chemistry in the y-axis, I find there are only 3 quadrants are fulfilled. We have chem-chem in the top right quadrant with the detailed chemistry but intense computation costs. We have Chem6 in the bottom right quadrant with the same complexity in the dynamics, but with very simplified or just simply no chemistry. But in addition to that, we also have this idealized climate model with lower complexity in the dynamics. For example, we have this aquaplanet that are idealized configuration of the global atmospheric model in which the planetary surface is water covered. And in most use cases, the surface temperature in the aquaplanet is prescribed to some simple analytic distributions in latitude with no variations in longitude. And the utility of this aquaplanet configuration lies in its simplicity because it removes the interaction with the land surface and reduces the dimensionality in the climates. So it serves as a crucial level in the hierarchy of the model that is needed to understand this complex climate system. The idea of building the model hierarchy is widely used in the climate models, but not yet applied in the chemistry climate model framework. Therefore, I create this AquaChem model, and this model will be positioned in this remaining top left quadrant that will have a much lower computational cost, but it retains the full complexity of the chemistry. And this AquaChem is actually built on the aquaplanet configuration by incorporating the detailed chemistry and emissions. So compared to ChemChem, AquaChem is using this prescribed annual zonal average symmetric sea surface temperature, which maintains the pole to equator energy gradients that drives the Hartley sail and the upper tropospheric jet. However, the setup of the zonal average SSTs will eliminate other climate dynamic patterns, such as shifts of the ITCZ zone or the water circulation. In addition to that, we'll also further simplify the emissions. And across all of these 103 emission inputs, we calculate the annual zonal averages of the emission and remove the spatial and the seasonal variation within the emission inputs. So with the simplification in both the climate dynamics and the emissions, a good side effect of this AquaChem is that it substantially reduces the dimensionality, it substantially reduces the computational cost through shorter integration time because of this lower dimensionality in both climate dynamics as well as the emissions. So this is a configuration of the AquaChem. Next, I want to demonstrate that the AquaChem is actually useful for us to understand these complex OH chemistry systems. And here we conduct a lot of different validation tasks, but here I'm showing you that the AquaChem is able to reproduce the contribution of the individual OH production and loss pathways. Why we care about the OH loss and productions? This is because OH is so short-lived, so it's always assumed that the OH is at a steady state. So the OH concentration equal to the total OH production rate divided by the total OH loss frequency. And here, what I'm showing here, is the contribution of the individual OH productions versus OH losses, both from AquaChem on the left and the ChemChem on the left and AquaChem on the right, that is integrated between -60 to 60 latitude beams. So first, I'm showing this contribution of the individual OH productions, both from ChemChem and AquaChem. We show that across all different clusters of the reactions forming OH, there are 4 reactions that are most dominant, including this photolysis of ozone followed by the reaction with water vapor to generate 2 OH radicals, the reaction between NO and HO2, reaction between ozone and HO2, and photolysis of the hydrogen peroxide. And these 4 reactions alone contribute to a total of 92% of the OH production rate. And comparing against ChemChem, AquaChem successfully reproduces partitioning across different OH production pathways. We also examine the contribution of these individual OH loss pathways, and from the bottom to the top, it shows the OH losses through the reaction with CO, different HOY species, methane, multiple VOC reactions. And we show that even though the AquaChem tend to simulate the higher contribution of the OH losses from CO and underestimate the contribution of the OH losses from the VOC species, but they were able to reproduce these rankings of the relative importance of these individual OH loss pathways. So to sum up, we find that this AquaChem will serve as a very simplified but rapid tool so as to assess the changes of the individual OH budget terms, and in other words, help us to gain this process level understanding of the OH chemistry. And we use AquaChem to assess our original question, the OH response to the climate warming. So to do that, first of all, we run a present-day scenario using AquaChem, where the SST and the emissions are prescribed for the year 2000 condition. And we also conduct another idealized warming experiment by increasing the SST globally by 2 Kelvin with a fixed emission input. And this 2 Kelvin is the upper limit of the temperature increase by 2100 under the Paris Agreement. But as we mentioned before, there's also an indirect OH response to the warming through these temperature-sensitive biogenic emissions. But this is the part that remain highly uncertain. And in the model simulations, we use this mega emission scheme, which suggests that under the 2K idealized warming scenario, the biogenic emission will increase by about 37%. Therefore, we set another idealized warming experiment with the increase in both SST as well as its biogenic emissions, and use this idealized warming experiment and compare it against the present-day scenario to quantify both indirect and direct OH response to these 2 Kelvin idealized warming. But by comparing the first two simulations, we can assess how OH is directly responding to the warming through the changes in the meteorology. And by comparing the last two simulations, we can assess how these temperature-sensitive BVOC emissions will impact the OH budget. So getting to the results base, first, what I'm showing here is this joint distribution of the changes in the OH production rate in the x-axis and OH loss frequency in the y-axis under 2K idealized surface warming scenarios. And overall, we show that under the climate warming, there's an increase in both OH production rate and OH loss frequency, but they tend to convolute together. That's why if we when we further separate out the impact of the meteorology and these temperature-sensitive BVOC emissions, we find that the influence on the OH budget go to 2 dimensions. The meteorology primarily drives the increase in the OH production rate, while the BVOC emissions are the main contributors to the increase in the OH loss frequency. So next, we also want to address these regional variations. So what I'm showing here is this response of the OH budget terms separated by 3 regions, including tropics, southern extratropics, and northern extratropics. And what I'm showing first is this direct OH response to the idealized warming by characterizing the increase in the OH production rate, ranging between about 8 to 10% in total across these 3 different regions. And if we further diagnose what are the contributions of the individual OH production pathways, we find this OH primary production pathway contribute to about 6 to 8% of the total OH loss increase in the OH production rate. So these were basically the main contributor. And we also find that this 6 to 8% increase in the OH primary OH production rate is consistent with about 7% per K increase in the water vapor following the Clausius-Clapeyron equation. So from here, we can conclude this direct OH response to the idealized warming is pretty much dominated by these moistening effects. And moving to the temperature-sensitive BVOC emissions, we already know that the major impact is from the OH loss frequency. But if we look at the individual regions, we find that the increase in the OH loss frequency could be as high as about 13% in the tropics, which is almost double of the increase in the extratropics. And looking at the individual loss pathways, we are first looking at these reactions with these BVUC species, and it contributes to about 4.5% increase in the tropical regions. And this is consistent with the fact that tropic has the most abundant BVUC emissions. In addition to the BVUC species, we also look at these two different groups of the BVUC oxidation products, including the oxygenated VUCs and COs. These two oxidation products will also further react with OH and serve as the OH sink pathways. And if we look at the contribution of the OH reaction with oxygenated VOCs, we find that it contributes to about 2.2% increase only in the charcoal regions. And this is because these oxygenated VOCs are still relatively short-lived, so it's mainly from the local production. However, if we look at the CO, we find that the increase in the CO is not only coming from the local production, but can also come from the long-range transport because of this long chemical lifetime of CO. And this leads to about 4% increase in the OH loss frequency, mainly due to the increase in the CO in the southern extratropical regions. But overall, we find that these three different pathways, including BVUC and 2-BVUC oxidation products, are the main contributor to this increase in the OH loss frequencies. So to sum up, we find that this net OH response to the idealized warming, it depends on this competing process through moistening, which lead to the increase in the OH production rate, and these temperature-sensitive BVUC emissions that lead to the increase in the OH loss frequency. And how OH is actually responding to the climate warming really depends on which process wins out. And for the future work, we need a more accurate quantification of the climate sensitivity of these BVUC emissions in order to give us a good sign of the track on the OH response to the climate warming. And last, I also want to mention that this OH response to the idealized warming is just the first user case of this AquaChem. And now we are using AquaChem to diagnose OH sensitivity in other aspects of the chemistry climate system. And I also envision a broader applications of this AquaChem to look at other aspects of the chemistry climate interaction. So if you are interested in the OH or just the AquaChem, feel free to reach out to me through my email. Thank you.
Time for a question?
On the AquaPlanet. Does this run have interactive fin and CIs model?
Unfortunately, we don't have the CIs in the model. That's why we confine our analysis region to -60 to 60, because in the higher latitude, in the absence of the CIs as well as our temperature gradient, it would generate a very unrealistic climate dynamics.
And so the albedo is that somehow prescribed?
Yes.
I don't know anything about the AquaPlanet setup.
Yes.
Okay. All right. Thanks.
Okay. One more question? Yeah.
So you're looking at the troposphere as a whole, is it right? I'm wondering if you look at like separated, like in near surface or lower troposphere or upper troposphere, if you get different answer, because the OH source and sink is quite different near surface and the upper atmosphere.
Yes, I did. So actually, my another piece of the results is also separate them across different vertical beams, and I further separate them between I think with the pressure larger than 600 HPA and the pressure larger than lower than 600 HPA. And we do see the difference, especially over the tropical region, because in the upper troposphere, in the tropical regions, we still see these moistening effects wings out. But near the surface, we see a larger impact from these BVUC emissions because, as we expected, these BVUC emissions will be more follicles near the surface, closer to where the source is.
Thank you. Excellent. Thanks. Let's move on. Thank you so much. Our next speaker is in a time zone where it's getting very late. Adriana Bosilosco is going to talk about short-lived halogens.
Okay, let's share my screen. Okay, I am trying to share the screen. I don't find.
If you continue to have problems, I could potentially share it.
It's the arrow
Oh,
down.
here. I found.
Got it? Okay.
Okay. So now you can see my screen.
Yep.
Yeah, we see your full
Okay.
screen.
Okay, thank you.
Can't see your slides though.
Okay, so I will share our research on the key role of short-lived
Adriana,
halogen.
sorry,
Yes.
we cannot see your screen at your
No?
slide. Not your slides. We can see your screen, but not your slides.
Okay. So sorry, I will start share. I think I shared the all the maybe now. Now, yes.
Yes, we can see your
Okay.
slide, and it just needs to be in full screen.
Yes.
Perfect. Thank you.
Okay, right. So I will share our result of the key role of short-lived halogens on global atmospheric oxidation during historical period. This work was carried out in the Atmospheric Chemistry and Climate Group in Madrid and in collaboration with Infinoa CONICET from Argentina. I would also like thanks to all of my co-authors. So to start, short-lived halogens are reactive allocarbon species that have relatively short lifetime in the atmosphere, typically from days to months. So therefore, they participate in different reactions in the atmosphere, affecting the abundance of different oxidants and affecting the chemical composition. So there is several previous work that investigate the role of SLH in some specific process or region, but remains an comprehensive global assessment of the impact of SLH in the abundance of atmospheric oxidant during historical period. So to address this, these studies focusing on three objectives. The first one is improve the knowledge of short-lived halogens on the atmospheric oxidation capacity. Second one is include the last advancement in the SLH chemistry, including both natural and anthropogenic source. And third one is analyze the implication that SLH has in the principal oxidants like OH, ozone, NO3, and chlorine. So to carry out this work, we're using the CSM 1.2 model with the SLH chemistry in CamChem. We conduct 4 sets of simulations running for a period of 5 years, representing the pre-industrial period and present day. And for each period, we include the SLH chemistry and emissions, and we run another 2 kind of simulation without this SLH chemistry. So our model includes both natural and anthropogenic source for SLH. Furthermore, we also include the heterogeneous recycling of inorganic allergens reservoirs on sea salt aerosols. And also we update in CamChem production from chlorine from mineral dust sea salt aerosol. This is a picture of this mechanism that was based on the work of Van Herpen et al. 2023. Briefly, in this mechanism is proposed that blowing iron rich dust from the Sahara out over the Atlantic, mixed with the sea salt Sprite and forming the MDSA particles. Then the iron goes oxidation and transformation, and then this activated iron reacts with the chlorine from sea salt. And when the sunlight reach this particle, it triggers a reaction that can liberate chlorine atoms, and then these chlorine atoms can react with other atmospheric gases. So these tables summarize our 4 set of simulations for pre-industrial and present day without and with SLH. So for example, in pre-industrial, we only have a natural SLH emissions. And for anthropogenic and biogenic emissions other than SLH, we keep contact for the period in the simulation without and with SLH. So going now to the global change of atmospheric oxidant in pre-industrial and present day. So the impact of SLH is highly dependent on the local environment. So for example, in clean environment, the allergens can deplete ozone, and this leads to a decrease of OH, but in polluted environment or continental regions, SLH can increase the OH formation due to principally the photolysis of allergen acid, and also the oxidation of VOCs that form ozone. So our results shows that SLH reduced the tropospheric ozone burden by here 20% in present day and 21% in pre-industrial period. And this reduce or indirectly reduce the tropospheric OH burden in a 30% in present day and in a 70% in pre-industrial. So beyond of OH and ozone, there is also a reduction of NO3, principally due to the depletion of ozone. And we see that also the relative reduction of NO3 is larger in pre-industrial, but the levels are much lower due to the lower NO2 levels in pre-industrial period. In the case of chlorine, the burden is increased in both periods, in present day and in pre-industrial, but there is a larger increase in chlorine in pre-industrial periods. And this is because at present day, there is a larger fraction of chlorine that is stored in reservoir species because there is a higher NOx and HOx levels from the anthropogenic emissions in the present day. So if we see the global or spatial distribution of this change, here this plot shows the percentage of difference for present day and pre-industrial due to the SLH for each oxidant. And as we say before, we see a large decrease of OH and ozone in remote and clean environment like oceans. But there is also an increase of OH in polluted continental region, principally in the northern hemisphere. And this is because SLH also induce the OH formation through the photolysis of the halogen acid and the increase of OH ozone formation. In the case of chlorine, as we saw before, in both periods there is an increase for chlorine, principally in regions with abundant dust and sea salt aerosol. And also the increase of chlorine is more pronounced in pre-industrial period because there is lower NOx levels that favor the formation of reactive chlorine species. So we next investigate how short-lived halogens impact in the chemical pathway for the OH formation. So we know that the OH is primarily formed through the ozone photolysis of ozone. This is called primary source. But also there is secondary source for the OH formation that arise from reactions with NOx, ozone, VOC, and of course the photolysis of halogenated acid. So in this table, we show the contribution integrated in all the troposphere for our 4 cases in present day and pre-industrial. And we can see that the inclusion of SLH leads to a reduction in the primary production of OH due to this ozone depletion in both periods, in present day and pre-industrial. And there is an increase in the total secondary OH production, attributed principally to this new pathway for OH formation. Looking now the global distribution of this change, here I show the difference for the primary production due to the SLH and the secondary production, the total in present day and pre-industrial. So we see the largest reduction of primary source in the tropical regions, where the primary source is the dominant source for OH. But there is also an increase of secondary source in the continental regions, more in the northern hemisphere again. And if we compare the change in the present day with the pre-industrial, the change in pre-industrial are lower because we have less NOx emissions in pre-industrial, and also because there is no anthropogenic SLH emissions. We also calculate the OH recycling probability, that is a concept that was introduced by Lilibet 2002, and reflects the proportion that of OH that can be regenerated from its secondary source. So in our simulations, we see that in both periods, in present date and pre-industrial, here is, in present date and pre-industrial, SLH increased the recycling probability. And looking the geographical distribution for this recycling probability, it's observed that the lower values are in the tropically regions, where OH is highly depend on its primary production, and the values of air reach or are higher than 60% in the northern mid-latitudes. And in both cases, in both periods, SLH increased the recycling probability between 2 and 4% in continental regions, and between 10 and 16% in the tropical and oceanic region. So for one side, we have that SLH decreased the OH level, but also enhanced the secondary production for OH. So at some point, SLH increased the natural resilience of the atmosphere to the external perturbation. Last, we investigate how the addition of SLH impact the burden of different VOC, due to that there is a difference in the reaction rate of VOC with OH and chlorine. So this plot here in the upper panel shows the percentage of change for the VOC concentration due to the short-lived halogens. And the bottom panel shows the percentage of each oxidant to the loss of this VOC. So as we said before, SLH reduced the OH levels, and this reducing of OH levels leads to the increase of some important VOCs like CO, methane, isoprene, and propene. And this is because if we see this plot for these VOCs, the dominant loss is due to OH. So due to that OH is reducing, these VOCs are increased. And the opposite behavior is observed for example, ethene, propene, and big alkanes, in which the loss due to chlorine is the dominant loss for this VOC. So as chlorine increase, these VOCs are reducing. So to summarize, our results shows that SLH reduce the oxidation capacity, primarily because they reducing the concentration of the major oxidant like ozone, OH, and NO3. This reduction of this impact is more pronounced in pre-industrial period, where SLH account for a quarter of OH and a half of NO3 in the boundary layer. For the other hand, SLH increased the OH recycling probability and reduced the dependency of OH on its primary production. There is a complex interplay between the oxidant, SLH, and VOCs that leads to substantial change in the burden of some key organic compounds, which have implications in air quality and aerosol formation. And all of these underscore the complexity and multidirectional chemical interactions between SLH and atmospheric oxidants, and the needed to incorporate the detailed SLH emission and chemistry into air quality and climate models. And that's all.
Thank you.
I will come back here.
We have time for one quick question. Yeah, go ahead.
So when you include the chlorine chemistry in the pre-industrial and present day, does that change the ozone climate impact going from pre-industrial to present day then? I don't think you showed that. Maybe I missed it.
Did you see that if this chlorine changed the ozone levels?
Yes,
The climate impact is what.
climate impact.
You referred to lifetime or something, I don't know.
Now, going from pre-industrial to present day, ozone's going to increase. And so depending on your halogen mechanism, it's going to increase differently. And I was just wondering if the chlorine feedback on OH, if you get more ozone or less going from pre-industrial to present day.
I don't know. Good question.
Okay.
Yeah, let's follow up about that. Okay, thank you. Let's move on. Beirut Rosita is going to continue the discussion on sulfur intelligence. Oh, yep, perfect. Thanks. So yeah, Beirut is going to continue the discussion on short-lived halogens. And he should be online.
Hi,
Hi.
do you hear me well?
Yes, we can hear you and we can see your slides.
Okay. So hi everyone, my name is Beirut Ruzitalab, and instead of trying to present multiple works, we decided to give an overview of the studies that we have done on short-lived halogen model. So in this talk, I will talk about basically 4 studies. I will try to summarize that. And, my apologies if I missed some of the details. So Doug showed this figure yesterday that shows the impact of halogens and what's happening because of them. So we have the long-lived halogens that are being controlled successfully over the years, and now the attention are going toward the short-lived halogens, and one specific group of them that are called very short-lived substances. And because of the CSM short-lived halogens development, thanks to Rafa Fernandez and Alfonso Saiz Lopez group, now we can do more studies and try to investigate that. So in this figure, we see that there are some sources from anthropogenic sources or natural sources that they emit halogens to the atmosphere, and then they release radicals, and it can impact ozone in this figure. But if we go further, the impact on ozone, as we saw in the previous talk, it can affect the OH, and then as a result, we have a competition between OH oxidation and radical oxidation. Then it can impact methane and other VOC oxidations. So in this talk, I will talk about these 4 studies that we are trying to look at different components of this scheme. In one study, I will talk about the distribution of some anthropogenic sources and their impact, their distribution in the atmosphere. Then I will talk about I will talk about the emissions of two of these oceanic sources, and then I will talk about the impact of the short effulgence on the atmosphere, with specifically on methane, and then their impact on some VOCs and their potential impact on aerosols. So in one study, we try to look at, I will show only the results for one important compound, which is called dichloromethane, or CH2Cl2. And on the map, I'm showing the emissions of dichloromethane on the background, where we see large emissions over Eastern Asia, and then some over Europe and North America. And then the overlay is showing the measurements that we had. And the goal of this study was to evaluate the performance of the short-lived halogen model. And we were using the earlier version of this model in CSM1. And on the right panel, I'm showing one of the results that shows the vertical profiles of different measurements in different dots, and the model in the blue line, and for different latitude beams. And so, long story short, is that the model was capable of trying to simulate the interhemispheric differences and show also the vertical profile of this compound in the atmosphere. And so, which is very interesting for us. And then we try to go further and look at the impact of different source regions. And so we did tagged sources analysis, which we found that 70% of the atmospheric abundance of this compound is basically because of the emissions in Asia, and most dominantly from China. And here we are seeing that the zonal plot of annual mean, we see that it's ubiquitous. It's available everywhere, from the Antarctic to the polar regions. But then we wanted to look at the different altitudes and see how they change, and which sources, which regions are important for the transport of these compounds in the atmosphere. So with here I'm showing the maps for each of these sources, on the left for surface, and on the right for upper UTLS, upper troposphere. And then there are small font sizes, but the conclusion was that we saw the importance of Asian emissions again on the upper troposphere, and they were contributing dominantly to the transport, to the global transport of these compounds. And this paper is published, so you can find more details in the paper. But then on another study, as I said, we wanted to look at the natural sources, and the reason for that was that in the WMO ozone assessment report, there is a question that although we know that they are emitted primarily by oceans and natural sources, but what's the impact of anthropogenic emissions and and human activities on the emissions of these natural sources. So we developed a framework using a machine learning framework to produce this oceanic concentration from these for these two compounds, specifically bromoform and dibromomethane. And then we use the air-sea exchange, air-sea transfer module within the CSM and the SLH model to calculate the emissions of these compounds and their impact on the atmosphere. So here I'm showing like the results for the changes of bromoform on the left map and dibromomethane on the right at the end of the century. And we saw like large increases over some certain regions, specifically over tropical Pacific, Western Pacific region, which is a main pathway for the transport of the compounds to the upper troposphere. And overall, we estimated that based on this scenario, the emissions of bromoform and dibromo can increase by up to 30% to the future. So what it means is that if the emissions are going to increase in the future, and we know that for example, Asian summer monsoon is going to enhance in the future, so it means that we will release more halogens to the upper troposphere. And here we looked at the changes of the impact of this emission change on the upper troposphere bromine from these two compound source gases. And we see that the seasonal performance, the seasonal evolution does not change a lot between present day and future. But in terms of the absolute values, we saw up to 50% enhancement in the bromine from source gases, which is significant. Then I would like to talk about this study. And we saw in the previous talk that the impact of the short-lived halogens on the oxidation capacity and on OH. So the goal of this study was again to investigate that, because we know that methane emissions are increasing in the future, and so we have to know what like the whole chemistry of the methane and their sinks, and what are the impact of the OH on methane, and what is the impact of the halogens on the atmospheric chemistry. And here on the right, you are seeing the on the top, it shows the methane surface concentration prescribed from CMIP6 that is currently in the model. And on the bottom, we see the prescribed flux from the available data sets, which shows very different distribution. So in this study, we looked at the CSM2 model with and without the short-lived halogens. And we also looked at the impact of the prescribed methane at the surface, or using the emission-driven methane from different data sets. And the simulations were done for 5 years, and mostly trying to focus on evaluate the model against ATOM campaign. So this is like one of the main figures that shows that with inclusion of the short-lived halogens, we basically we reduce the ozone in the atmosphere, and as a result, the ozone loss is also decreasing, which means as a result, if we have less ozone loss and we have less OH production. And as a result, we see the methane sink through the OH oxidation decreasing, specifically over the tropical regions. And quantitatively, we estimated that the chemical loss from the methane was decreased from 575 trigram to 520 trigram, and which means that we basically were able to increase the methane lifetime by around like 1 year, the tropospheric lifetime. And here we show that like the methane and monoxide, the CO measure observations and the model performance in simulating those. So there are different scenarios included in this in this plot, but like to summarize, we see that these very systematically biased low values are from the model without short-lived halogens, and by including the short-lived halogens, we get closer to the observations from the satellite. And on the bottom panel, we see the results for CO, which again shows the similar results, that we are getting closer to the observations. And although there are still some uncertainties, but these plots confirm that the inclusion of the short-lived halogens in the model certainly improves the CO and methane representation. And in this last study, we are trying to look at the impact of the chlorine and the radical like chlorine radicals on the some VOCs, and specifically on volatile methylsiloxanes that are released primarily from personal care products. So one of the major compounds, it's called like shortly as D5, and recent studies using the lab experimentals, they found an additional oxidation pathway using the chlorine, and they found that they estimated 5% removal oxidation of D5 is through chlorine radicals. And it can, the oxidation product can also then go through the gas aerosol transfer and produce secondary organic aerosols. So in this study, we developed the emission inventory for D5, and then try to look at the distribution of D5 and its oxidation products. And one interesting thing that we found was that although the lab experiment predicted about 5% oxidation through chlorine, the model showed about 20%, so it's much larger, and it's one of the interesting results. And then we also looked at different simulation and experiments. And so on the left, I'm showing the D5 monthly concentrations on the left and D5 lifetime on the right. And if you only look at the difference between orange color and red color, we see that by inclusion, the short-lived halogens and specifically chlorine radicals, we estimated that global concentrations decrease by 20% and lifetime increases by like 45%. 5% in general. And yeah, so this was like a very fast overview of 4 studies. And with that, I'm happy to answer your questions. Thank you.
Time for one quick question. Yeah. go.
Beirut, really nice talk. For study number 3, do you know what the methane lifetime is when you include the halogens now?
Yeah, I think, yeah, Ben can confirm that, but I think with the inclusion, it's like 9.5.
9 to 10. You get in 1 extra year.
Wow, that's really good. We've
Yeah.
always been so low. It's nice to see that. Yeah.
Yeah, that's why you see the MOPIT CO and it's mentioned.
So short-lived halogens are important for methane lifetime.
Yeah. Well, thank you.
Thank
Yeah,
you.
just a bit.
Okay, we're moving on to our final talk before the break. Julian Villamere will talk about methane thiol and aerosol cooling in the Southern Ocean. And Julian is also online. We had to move a few remote to this early session because of time differences. So thanks for staying with us.
Okay, so
This may be interesting. This may be interesting. This is- No, I mean, it's a lot of
oh, I'm sorry.
Yeah.
Okay, do you see? Can you see my slide and you hear me correctly?
Yes, we can see your slides and hear you.
Okay, thank you. So my name is Julian Villamayor, and I work in the Spanish Research Council in the Atmospheric Chemistry and Climate Group, led by Alfonso Said Lopez, who you may know better. I am presenting here an assessment of the effect that marine emission of methane thiol has on climate, particularly in the Southern Ocean. This methane thiol is a well-known oceanic source of sulfur, but however, its effect in the atmosphere has been so far overseen. I want to mention that this work has been led by 2 groups of the Spanish Research Council. One is the Chemical Physics Institute in Madrid, where I work, and the other one is the Institute of Marine Science in Barcelona. And we also work in close collaborations with other colleagues from Argentina, India, France, and so on, that I also want to acknowledge. Well, the ocean emitted dimethyl sulfide, the DMS, is well established to be a major source of sulfate aerosol that cools climate. This cooling occurs via the oxidation of in the atmosphere to intermediate products that lead to sulfur dioxide, (SO2) formation, and ultimately sulfate aerosol that interacts with solar radiation, scattering sunlight directly, but also indirectly by increasing the cloud albedo. Well, while the DMS is a significant marine biogenic sulfur compound, marine measurements show that DMS only represents around 15% of the marine biogenic sulfur cycling. In turn, the largest portion of marine biogenic sulfur cycling is routed to methane thiol, which is another volatile sulfur compound. However, despite the proven relevance of the methane thiol formation, its high reactivity to metals and surfaces, especially, has challenged its measurement in seawater. So, in contrast to the DMS, global scale mapping of methane thiol concentration or C2 air fluxes are not available so far. Hence, the global emissions and climate impact of the methane thiol remain unexplored so far. But yeah, okay, sorry. But in this work, our colleagues from Barcelona nicely achieved to compile a global field of methane thiol, and we have been able to assess these effects, including this field of methanethiol in the CAMCHEM model. Well, to compile the seawater methanethiol concentration, our colleagues from Barcelona used measurements of the few available campaigns that measured concurrently methanethiol and DMS. These are these few campaigns in the Atlantic, in the Nordic Sea, and also in the Northeast Pacific. They were also able to include new measurements in the Southern Ocean and the Mediterranean Sea. This way, they found a strong correlation between the methanethiol and the DMS concentrations that was even improved, distinguishing two clusters of different oceanic regimes, depending on SSTs and the bathymetry. Broadly, they've defined a high regime for open ocean and a low regime in regions of continental shelves or warm SSTs. These two regime empirical model allowed the construction of global fields of climatological monthly methanethiol seawater concentration from global DMS, observational SSTs, and bathymetry. Finally, combining the resulting fields of the seawater methanethiol concentration with concurrent data of SSTs and wind speed at 10 meters, there are the variables on which the sea-to-air flux depends most. They were able to calculate the sea-to-air flux of methanethiol, which resulted in 5.7 teragrams of sulfur per year. The resulting methanethiol flux exhibits strong seasonal and regional variability, peaking in high latitudes during summer, similar to DMS. However, the ratio of methanethiol flux to the total volatile methylated sulfur, that is the methanethiol plus DMS budget, varies significantly across regions and seasons. But globally, the results show that the methanethiol contributes 19% to the total biogenic sulfur emission, with the Southern Ocean as a major source, contributing approximately 27% of the global methanethiol emissions. So now that we had our new and complete global emission inventory of methanethiol, we were thrilled to know about the effect it may have on the atmosphere and ultimately on climate. So for that, we used the CAMCHEM model. But first of all, we had to update the chemical scheme of sulfur in the atmosphere, including the reactions associated with the methanethiol, following these recent works, including the main reactions leading to SO2 formation. We performed specified dynamic simulations with the radiative transfer model that allowed to quantify the radiative effect of the sulfate alone, and reproduced 5-year climatologies. Finally, we conducted 2 simulations with the same configuration, but including or omitting the methanethiol flux. The simulations revealed that adding methanethiol emissions to the model increases the budget of the total volatile methylated sulfur globally by 34%, but particularly in the Southern Ocean, where the increment is 51%. When splitting this increase in the budget between methanethiol and DMS, we surprisingly found that even though the DMS emission remained unchanged in one and another simulation, the DMS atmospheric budget was also increased. So we found that this is because of the faster reactivity of methanethiol compared to DMS. actually. So because so in the presence of the methanethiol, oxidants that deplete DMS decrease, increasing the local chemical lifetime of DMS by more by more than 1 day in the Southern Ocean, lower troposphere. In consequence of the extended lifetime of the DMS, the total volatile sulfur propagates more widely to higher levels and latitudes to the pole. So the wider distribution of volatile methylated sulfur is coherent with an increment of SO2 production over the Southern Ocean, represented here in colors, doubling its budget near the surface. At the same time, this effect also enhances significantly the formation of sulfate aerosol, represented in contours, up to 70% here near the surface, around 65 degrees south. The increment of sulfate aerosol extends notably throughout the southern hemisphere, with up to 10% additional sulfate aerosol in the middle troposphere all across the Southern Ocean. Coherent with the strong seasonality of the methanethiol emission, the increase of both the SO2 and the sulfate aerosol also peak in summer, with up to 50% increase on average in the Southern Ocean lower troposphere. Associated with this large increase of sulfate aerosol, our simulations revealed an annual mean increase in the sulfate direct radiative effect of 28% average all across the Southern Ocean, with a peak of up to 50% here, around 65 degrees south. Also, the direct radiative effect has a peak in summer, with a maximum effect of minus 0.075 watts per meter square. Also, globally, the annual sulfate radiative cooling induced by methanethiol emissions is notably lower in relative terms, representing a 4%. This is because of the large anthropogenic contribution to the total global burden of sulfate. However, this apparently small contribution of the methanethiol to the global radiative effect can be considered as a residual value, because in absolute magnitude, this 0.016 parts per meter square is equivalent to about 1/3 of the net warming effect caused by the mitigation of anthropogenic SO2 emissions all over the last century. To sum up, this work presents the first database of global monthly C2R emission of methanethiol available to date. Its implementation into CAMCHEM reveals that the methanethiol emissions has a net radiative effect with important implications, especially in the Southern Ocean. We find that methanethiol increases the atmospheric burden of volatile methylated sulfur and sulfate aerosol because its high reactivity that effectively reduces the oxidants in the atmosphere, in particular OH, which is the major atmospheric oxidant of methanethiol. In consequence, the DMS and its oxidation products are transported farther away of the emission source, towards the equator, the pole especially, and to higher altitudes, which increase the intensity and the extent of the sulfate aerosol radiative effect. Besides this, the methanethiol effect on the atmosphere oxidative capacity can also potentially affect other atmospheric species that contribute to the radiative balance. This is such as halogens, methane, or secondary aerosol formation. So our results highlight the importance of including the methanethiol in global climate models for an accurate assessment of the atmospheric oxidative capacity and also the radiative balance, particularly in future scenarios of global warming as the anthropogenic sulfur emissions continue to decline. But the implications of including methanethiol in global climate models can even go far beyond what I've mentioned before. In this work, we have evaluated the direct relative effect of sulfate aerosol, but there is also an indirect effect through the interaction of aerosols with clouds that, according to the literature, can be between 2 or even 15 times larger than the direct effect. This means that the indirect relative effect of methanethiol can be estimated between -0.3 and -1.5 parts per meter square in January. However, both the particle formation and the interactions with clouds are a major source of uncertainty in global climate models, which on average have a bias in the simulated relative balance, which with an excess of incoming solar radiation in the Southern Ocean in summer that is between 4 and 15 parts per meter square. Therefore, the inclusion of methanethiol should also contribute to reduce, at least partially, this important bias in climate models. Well, just mention that this work has been recently published in Science Advances, and thank you so much.
Thank you, Julian. We have time for a question. Yes, Simone.
This was done, you said, with Chem 4, is that right? Again?
Yeah.
So what does it, can we implement it in the recent versions of the model as well?
Yes, we should, I guess, yes.
And what would that take? Or is that the plan that it would be implemented in like Chem 5 or 6, I mean Chem 6 or 7?
Yes, well, so far we're working with Chem 5 and
okay.
I don't know, but yes.
Yeah, so then it shouldn't be a problem. So it can be implemented easily. Great.
I think so,
you.
yeah.
Very interesting.
You're welcome.
Another question? Okay, if not, let's thank all our speakers again for this session. And we have a break now until 3:20.
Okay, so why don't we restart? So the first talk for the second session this afternoon is given by Luisa, and the title is Evaluation of Musica version 0 Simulations of Southeast Asia Air Quality.
Who's sharing?
No, do I need to start?
Yep.
Yeah, okay.
If I
Like, you know, oh, she's coming tomorrow, right?
I think so. She is not feeling well.
Yeah, I know.
So she sent me an email. Not sure if you will join today.
Okay. Okay. So I'm going to give, talk a little bit about what we're doing, with analysis of a field campaign called the Asia AQ, but I'm going to start with an overview of Musica because we realized we haven't really given any updates so far in this meeting. And probably most of you have heard about Musica for years now, but just in case, very simply, the goal of Musica is to combine, to provide multi-scale modeling of chemistry from incorporating what we can do with ForthChem down to 1 kilometer scales through CESM global multi-year century sort of scale. We have a Musica web page if you're not familiar. Find that, and we have newsletters that have quarterly updates of our progress and links to all sorts of other information. So Musica is being connected with SEMA, the System for Integrated Modeling of the Atmosphere, which maybe was mentioned sort of in passing on Monday, which is integrating across scales the atmosphere model. And as we learned in lunch, at lunch, things are moving along very quickly, are progressing, and there may actually be a SEMA model to run before too long that includes the ability to switch between the MPAS and spectral element dynamical cores and provides the coupling to the modular components of the physics and chemistry, and Musica incorporates gas phase chemistry and aerosols. So we're hoping that this will really allow us to share, swap different parameterizations in physics and chemistry. So this is our the current status of the Musica software development. So central to this is the Musica library, which includes components for chemical mechanisms, which we call MICM, the Model Independent Chemistry Module, and a variety of mechanisms are currently available. TOVX is a new photolysis scheme, which maybe could be swapped out for another photolysis scheme called CloudJ that being implemented in parallel, and the aerosols are still being built as part of this library. So then this will connect to interfaces that then allow the chemistry and aerosols to be connected to any atmosphere model. CAM-SEMA, the NOAA model, they're calling CAT-CHEM, standalone MPAS, and we also have a version connected to a box model we call MusicBox. So these pink boxes are being contributed by the Harvard team. So HETP is an update of Isoropia, which is a gas aerosol exchange scheme for aerosols formation. HEMCO is the emissions component, which is currently connected to CESM, but it will be connected in this framework as well, and the GeoChem chemistry model. But one of the primary goals of Musica is to do multi-scale modeling, and we can already do that in CESM. So we label CAM-CHEM with the spectral element, Musica V0, and you can make a regionally refined grid with that. And Musica V1 is CAM with the MPAS dynamical core, and you can also make a refined grid with that. And so that's being tested. We've been using Musica V0 for a number of years. And if you want to use Musica and have not yet started, we have a wiki page with tutorials and documentation. And there are a number of grids available already in CESM, the CONUS grid, this Arctic grid, a Greenland ice sheet grid. And you can make your own grid, and there are instructions on the wiki, such as this grid for with 1/16th degree resolution over Michigan that Nori's made. And Musica V1 is being tested. I'll say a little bit more about that in a bit. Oh, and you can put multiple regions into one grid. I've tried that. One highlight that we didn't get to on Monday, Rebecca has a grid over Australia and has been looking at the enormous fires in 2019, 2020 and their impact around the globe. And so there's a regionally refined grid of 14 kilometers off Australia, over Australia, that will help refine the chemistry and transport of those fire emissions. So I'll just move on to some of the work that we're doing right now is to analyze the field campaign, a field campaign from last summer called Asia AQ, I know last spring, just about a year ago, led by NASA. And it was designed to provide validation and science related to the geostationary satellite GEMS over Asia. There's the background picture here. And aircraft measurements were made in Manila, the Philippines, Seoul, South Korea, and in Bangkok, with overflights over Taiwan. And there are a number of ground-based measurements associated with it, and connecting to GEMS and other satellite measurements. So the campaign consisted of a few flights in each of these locations, And the white lines show the NASA DC-8 flight track that did profiling in the lower troposphere. And the colored patches show where a high-flying aircraft sampled with the geostationary instrument similar to the GEM satellite, and so could map out NO2 and formaldehyde over the urban regions. And there are only a few flights in each location, but they're very different situations on each of the flights. So it's really an exciting data set. And if anyone's interested in looking at Asia air quality, I highly recommend you start looking at this data set. The data is all available on the NASA archives. So one of the things that we're looking at is, so we provided, our group provided forecasts during the field campaign with Musica and with work with tracers. There are a number of other forecasts, but now we're moving on to evaluating the model with all these observations. And as usual, a key problem with these simulations is getting the right emissions inventory. And these plots here on the left show different emission inventories for Bangkok and show that they're greatly different. We have an inventory put together here on the left by the local group in Thailand. And so hopefully that's better. We're just working on implementing that. So we're going to be comparing these different anthropogenic inventories, or also different fire emissions inventories, which are particularly important in Thailand to this time of year, and try to come up with an optimal set. And Ben is also going to help by doing data assimilation with Musica V0, with the Tropomi NO2 and CO to try to optimize and help evaluate the emissions, as well as provide comparison to other years. So these are the fire emissions. We know fire emissions are very uncertain and they're very different between different inventories. So on the left here is the thin inventory that we produce here at NCAR. QFED is produced by NASA in real time, and they're very different for this one day in March last year. Some of the first indications are that the higher emissions are better. In the past, we've thought maybe they were too high. And so there's a lot of work to do to improve those and evaluate those. And another aspect of the emission inventories is understanding the VOC speciation. And we really don't have a lot of information from that. For that, usually emission inventories just provide total non-methane VOCs, and we have to figure out a way to split them up. And on the left panels here is an inventory created by a group in Korea for the field campaign. And on the right is the CAMS inventory from Copernicus that we frequently use. And one has very high propane, the other one has very high toluene. And so, these are reactive species that'll have a big impact on ozone formation and also SOAs. So it's kind of a big deal to get this right. Another activity as part of this whole field campaign and analysis is putting together a multi-model comparison, and Katie Travis at NASA Langley is leading this, trying to help her out. And hopefully we'll decide on one emission inventory to all use, and then from that we can get a better idea of optimizing that inventory. There'll be some conclusions because each model produces different results even with the same model. So this is just our preliminary comparison at one point in Thailand, and the models are wildly different and different from the observations. And in this case, we have two sets of observations which are also different. So there's some latitude in our model uncertainty, but it's still, there will be many challenges to try to figure out what's the right set of emissions and simulations to use. June is working on finding out how much ozone is produced from different sources. And she's done some runs where she's turned off the NOx emissions from a region and separately the VOC emission, anthropogenic VOC emissions from a region. And so these are some plots for turning off the emissions of NOx in the Philippines to see how much ozone is produced by the Philippines emissions. And the Philippines is very isolated, so this is a pretty simple case. So there can be transport of pollution from China. As you see between these 2 days, just 4 days apart, we have very different ozone amounts in the background that affect what the Manila air quality is. But in general, there's not a lot of other sources. And so on the bottom here, we can see that there's a nice ozone plume west of Manila. The airflow this time of year is from the northeast, produced by NOx emissions in Manila out to sea. And then there were also fires in the northern parts of the Philippines. What we really want to do is have tagged NOx as opposed to turning off emissions. And so we're working on that. We haven't yet to identify all the bugs in implementing this, but that's our goal. And we had been started with the T1 chemistry and realized that the T4 chemistry is probably quite sufficient for this sort of study and will be quite a bit simpler. And then Wenfu is starting to work on setting up Musica V1 with the MPAS grid, and she's moved the 3 kilometer to 60 kilometer mesh to be centered over to the Philippines and Taiwan. And I think this will be a really great test of the chemistry and dynamics to be able to resolve an urban region at 3 kilometers and test it with these observations. So that's very exciting. And as part of all of this, we are working on improving the Melodies Monet model evaluation tool, which is a Python-based tool that reads in the model, reads in the observations, pairs them. You just set up a text file and it matches them all. It's a little bit different from the ADF that we're all using for CESM evaluation, in that it specifically matches the day and time of the observations with the model so that we can do specific flight comparisons, surface observations, that sort of thing. And it's all set up to produce lots of plots and statistics. And Gabby Pfister has this running with the WRF Chem simulation she's doing for Asia AQ. And we have Moffett comparisons to WRF Chem, and then the difference plot showing that the model's much too high over China, but much too low in other places. And Melodies Monet also reads Tropomi NO2. And so having satellite comparison in parallel with the aircraft comparisons, we'll be able to say a lot more about the emissions and the chemistry and dynamics in these models. Very briefly, I'm planning to do some runs for HTAP. If anybody is interested in helping, they want, there's a version 3 to look at ozone, PM, nitrogen, and sulfur deposition. They have yet to provide the emissions. Last year, they said they wanted to have the simulations done by this spring to address the protocols that UN wants, but we're still waiting for those. So if anyone wants to help look at simulations, I'm happy to help do them, but there are going to be a lot of them. So please get in touch. And I will just close with our ChemChem, our chemistry with CESM with chemistry wiki page has a section for current users and now with development plans. So if you have anything to contribute, if you're working on anything, like some of the things we heard about today, let us know and we'll put it on the wiki page, and hopefully we can help will help us all communicate. Any questions? Additions?
I just wanted to add this. We are thinking that this is really not ChemChem only, but should include WCAM. And I'm just thinking about WCAMX too, because there's chemistry that we are hearing about and discussing. And it's the page that helps people to set up. And I mean, we wanted to make it broader. Martina couldn't be here, but we discussed it earlier too, also, right, with others from the WCAM team, that it's really a website for chemistry users and, you know, in the whole atmosphere.
Yeah, it's information that's probably all buried in the CAM user's guide somewhere, but
Yeah.
that's harder to keep updated, and so we hope that people find this useful.
Yeah, and it has here chemistry climate working group. It can have WCAM, right? Rebecca is also
we could
in maintaining it if there's interest, and that's all what we are saying. So, yeah.
I have a technical question. So the grid refinement you showed, are those musical capability or CSM?
This is CAM capability.
CAM capability.
Yeah, spectral. This is Musica V10 is the spectral element grid, and so they're all tools that are part of CAM or separate, but are used with it. So any version of CESM can make spectral element can use a refined grid.
And it's up to how many, like 3 levels, 4 levels, or doesn't matter?
Oh, refinements?
Yeah.
We go down to 4 at the most, from 1 degree to a 16th degree. So we really can't go below that. 7 kilometers is the finest we can go based on the physics.
Right. Yeah.
And we haven't tried it, but I think, you know, you could start with a 2 degree and would be even cheaper for most of the globe at 2 degree and go down. Yeah.
So you mentioned the Australian bushfires, and when you go regional and refine there, is there any kind of pyroconvective process in there that would bring the fires up into the stratosphere?
I'm talking with Dave, Dave Pearson, who looks at the pyro-GDs and has a record of the emissions from pyro-CDs, and so we're going to need to develop a combined emission inventory of like the pyro-CDs and the normal fire emissions that don't get up into the upper atmosphere. Yeah, but there's no, I don't think there's any, I haven't looked into it, but I don't think there's any like meteorology really do it enough.
Okay. Because under climate change, we're going to probably have more fires like that. I mean,
Yeah.
But just to follow up, so is the model actually the convection happens in those one by one? I mean, how fine do you need to go with the resolution to get those pyro, you know, the model produce some convection?
Yeah.
Well, you need to inject the heat, you know, there are parameterizations that could be put in the model that the DOE group has put the FRITAS scheme, you know, that's in WCAM into E3SM, but we don't have that yet for CESM that is based on the meteorology.
But does it make sense? I mean, if you're based on the resolution, like if you're in, you know, 100 kilometers, I mean, 1 degree or even 50, it's like,
well, this
would go regional.
you'll go regional. So
Okay,
you need to kind of adjust it for scaling.
Yeah, maybe that, maybe you can't get it down fine enough. I was just curious. That's a big science question. Wondering.
If you run large the meteorology, you might be able to get some correction.
So did you see a difference in the vertical distribution of fire CO
Oh, I haven't do that yet.
with Musica? Yeah.
Hey, for sure.
Ben, do you want to set up? If you can ask what Ben is.
Related to the earlier questions. So for nudging, my understanding is for this kind of nested, you're nudging a larger scale, right? So all the technology within the refined region, there by itself. So you cannot guarantee that there's like.
And do you want to come here to the front?
I'm gonna use my mouse to, so
Yeah, you can use your computer, but I don't know about the microphone.
microphone is here.
Fine, you have.
Okay.
But
The model is. Yeah, so there is a. Yeah.
So the next talk is by Ben Gobert, and it's an update on the CMIP7 forcing set. So go ahead, Ben.
yeah, thanks. So yeah, we started to look into the CMIP7 forcings. I'm going only to talk about biomass burning and anthropogenic sources. With the help of CGD, they downloaded the data and then we started to look at it. I'm also looking at emissions from camps and got some help by Amin in Arizona and many contributors from ECOM and the CGD. Just to give some background on the most recent period, there has been a shift of ozone precursors emissions from the latitude towards the equator. You can see this here, in the differences of ozone column from satellite observations between 5 years in the 2013 to 2017 compared to 2000. And here is the trends by MLS for 2005 to 2020 in a recent paper that we co-authored with Doug and the MLS team, Lucien Froidevaux at JPL. They found a tropospheric positive ozone trends that we reproduce better when we use the CELS emissions rather than the CAMS emissions with both WACAM and CAMCAM. So yeah, there was an increase, mostly ozone precursors here, NOx, especially in Southeast Asia, with rapid economical growth in India and other countries. For CO, there's been strong reduction in anthropogenic sources that we can monitor with MOPIT, and with the relative slowdown in the most recent period in the same regions, especially Southeast Asia. And for the MLS trend, here you have a very significant negative trend in the upper trough that we couldn't resolve as well, but still we could simulate them better with the CELS emissions rather than CAMS emissions. So I'm going to focus on the differences between those two inventories that are widely used, CAMS European that are based on EDGAR and CELS. Last but not least, there has been some new records about CO observations in ice cores in Greenland and Antarctic that you can see here. The black line is the CO observations in the Northern Hemisphere, so Greenland, that are then extrapolated to most recent period, and the observations from NOAA here. And IRCAM-MIP, so the previous CMIP model ensemble, is underestimating the CO for the entire period, and they reproduce that increase of CO that kind of max out in the 80s and then start going down, following what I was just saying before with the reduction in the most recent period. But the models do pretty well in the Southern Hemisphere. So yeah, that's some of the background. And then it would be interesting to look at these new data sets once the CMIP7 simulations are done. So here's the slide from the website. The CELS emissions are available at a half degree. They have different lists. So here for the main pollutants and then VOCs that are speciated, which is greatly appreciated for chemistry. And I did use the CSMFV at 1 degree. So I regraded those data sets and make them TS 1.2 chemical ready. And I haven't looked at the aircraft emission yet. So those are the SEDS version 2024. So here are the results. So you can see that time series of CO emissions in the northern extratropical hemisphere for CO and NOx, with that increase all the way to the 80s and 90s. And so it looks reasonable and in line with the previous CMIP6 study. So now I'm comparing with the posterior CO emissions that I developed based on the CAMS emissions. The CAMS are in purple and the SEDS emissions are in blue. So with the posterior emissions, I'm having higher CO emissions that are derived from a simulation for 2018. And so you can see that the blue line is pretty much in line with the CAMS emissions with a stronger decreasing trend, which is something we want. And for the NOx, they're quite higher in the SEDS inventory. And there is a CAMS mosaic that is available for NOx that I've been using also, but more for different simulations that I'm not going to present here. So these are also another point of comparison because they've been updated for Chinese national MEIC inventory by province in China and by NEI in the US. And so then you get a stronger negative trend using this inventory. They have started to produce the CO emissions, so it will be interesting to look at the trend here because they should get better compared to with stronger decreasing trend. So I've been using the posterior CO emissions, and I will do simulations with this emission inventory and simulation with the new SEDS emission inventories in blue. So I'm using the SLH representation that is being developed and will be submitted soon in that description paper that by Rafa Fernandez et al. And I did 4 simulations. The first one is concentration-driven and emissions, so standard CMIP6 somehow, with fin emissions for fire using this only because we're covering the longer period. That starts in 2003 here. And CAMS with update to CO that I was just showing. Then I did the same as simulation 1, but with emission-driven methane on Carbon Tracker NOAA. And then adding those 2 new simulations, one with SEDS 2024 for anthropogenic emissions only, and that starts in 2008 from simulation 1, branched. And then really like the last couple of days, I could get the fire emissions running, and I just did 3 years starting in 2015. But also including anthropogenic emissions, so it's comparable to simulation number 3. And so I'm using the SLH because you can better represent. So solid lines here showing the impact of SLH with the dashed lines. And then when you're using the posterior CO emissions, you end up having a much better representation in winter and spring CO. So due to both emissions that are higher and SLH chemistry that reduces OH biases, which is the unique sink for CO. So I'm just gonna go through this and compare with MOPIT CO. So this is again the northern extratropical hemisphere for CO and NOx. And then when you compare with CO, you can see that I could reproduce the same results that initial evaluation for SLH with pretty much an overestimation for the peak months, but a good representation in the fall and spring, and an underestimation in the summertime. The sales emissions that are lower are also underestimating, but they somehow quite well represent the peak in the winter, but they remain underestimated. So it means that the SLH doesn't completely solve the problem for the northern extratropical hemisphere bias in CO. Although it would have, it would have been probably worse in using just TS1. So this is for the tropics, so -20 to 20 north. Here, the sales emissions are lower for CO and higher for NOx. Yeah, so which is kind of interesting because the biases are a bit reversed. I mean, the spread is still quite large for emission inventories, but it's also what we're used to. Looking at MOPIT, the sales emissions are actually reproducing better with the posterior emissions that I'm using are a bit higher in this case, and so the combination of fin and sales emissions are doing very well in the tropics on average, which is very encouraging. Here for the US, so again, the posterior CO is higher, but here we have a very good agreement between the CAMS emissions and the sales emissions for most of the period. The stronger decline in CO in most recent years, which is probably more up to date. That's for CO, and for NOx, the sales emissions are much stronger trend that is based on NEI. And so the mosaic emission inventory that is using the NEI, but by state rather than emission totals, is also better reproducing that decreasing trend in NOx over the US. Well, the CAMS emissions are quite flat for NOx. For looking at MOPIT, our posterior emissions are performing very well. We still an underestimation in the summertime as like for the rest of the northern hemisphere. And the sales emissions are quite low. But this could be due to other things like the misrepresentation of the NOx, which could produce too much OH, and having a too short of a lifetime. I would be cautious using just a single model with a single chemistry to evaluate this, but it's still pretty reasonable compared to what we used to see in the previous version of the models. So this one is a bit more complex because we also have the Chinese emissions in green, and then the blue here is the sales emissions, again higher in the first decade, and then actually a pretty strong decrease in the second decade from 2010 to 2020, which is quite in line with the Chinese inventory, but the Chinese inventory is quite low in the first part of during the first decade. And then the CAMS emissions are very low compared to the rest. So there is a very important spread for during that decade, even though we have pretty good knowledge about this, and that we know that it's likely that the sales emissions we will be reproducing better. Then in most recent years, the emissions are much lower. So very, very rapid changes in CO emissions here. And the same for NOx. Then the mosaic inventory that is scaled to the Chinese inventory is obviously on top of each other. But there's still an offset in the NOx emissions that should be investigated more. And when we look at CO emissions, we do pretty well because we used to underestimate the Chinese emissions quite a lot. I mean, partly because it's been optimized by MOPICH here. So we overestimate the peak months again, but the sales emissions for that 2008 period onward is actually doing pretty well. For the whole country, there might be differences regionally. So look at ATOM, CO, and so the posterior emissions are doing much better and higher latitudes than for the sales emissions. So further from the source, the biases can be seen also in situ observations. But again, in the tropics, so now the colors are switched. So the orange is the sales usually in blue in previous plots. And the sales emissions are actually doing better in the tropics. So some of those things are from fires. And usually better in the southern hemisphere where we tend to overestimate CO observations. So this is in line with the MOPIT column observations. Quickly, the difference between emission-driven and concentration-driven. As you can see here, that the CO actually is not changed by using the emission-driven methane simulation. This is partly due because the methane emissions are fairly in line with the concentration-driven. And the comparison with GOSAT column showed that the emission-driven is actually outperformed the concentration-driven, which means that we could with confidence simulate methane with emissions better than the previous protocol of prescribing surface emissions. There can be artifact in the column. You can have differences between lower trope and upper trope. It's biases that would go in different directions. It needs to be tested with WACM or new vertical grid that are going to be available in CSM3. But oftentimes the emission-driven is better at reproducing the shape of the vertical profiles. Because, for instance, ATOM observations are in the middle of the ocean. So they don't have the same vertical profiles than the average that is used in prescribed that have a tendency to put higher methane at the surface because it's averaged between sources over land and the ocean. And so, yeah, as I was saying, recently got the fire emissions also. I think they're based on one of the version of GFED. I don't know if it's GFED 5 or not, or it's still GFED 4.1s. And so that's the yellow line here. And so here, kind of similar to what Luisa was showing, where QFED is lower than FIN, it shows that even though the blue was doing pretty well over the tropics, we now underestimate CO using the fire emissions from the CMIP7. So this is for doing NEO with pretty high CO sources in 2015 and 2016. So in a summary, I've been rereading the SEDS and the fire emissions from CMIP7 archive, and I've simulated them with CSM 2.2 1 degree FC nudge case. The SEDS emissions are consistent with what we know of NOx and CO over the last 20 years, but also for the historical period. There seems to be no problems with VOCs and other species that we don't look at much often. Although I should check for that the fire emission run has been well set up. And yeah, those results are pretty consistent with MOPIT even for 13 years simulation. The background CO is quite well simulated, but we tend to underestimate close to the source for US and China, especially in summer. And that CMIP7 fire emission seems to be lower than FIN, and low compared to MOPIT CO observations. So the emission-driven methane simulation is very encouraging. It's so far very consistent with the prescription of methane that was made in CMIP6. There will be also new surface concentration, and so it will be interesting to look at that as well, because that's probably why the emission-driven is performing so well, is because for the 2014 onward, it was scenarios that we were using and not concentration from observations. And I still need to process the aircraft emissions. So yeah, happy to take any questions.
Just a quick clarification. When you say methane driven, you always mean with the very short-lived halogens, right?
Yeah, they all have the same chemistry.
Yeah, they can, if we don't have the methane driven, wouldn't perform that well.
Yeah.
Yeah. Okay. But yeah, that makes sense. It's good to see. And does anybody, I mean, the information you have here, you get the CMIP7 data, right? That will be, we don't have any ways to change them anymore, but potentially we can give input.
Yeah, we can provide feedback.
Yeah, to the
Actually,
GitHub.
it might be it's probably more important for the fire ones, because there might be errors somewhere.
Yeah, so that would be good to give input.
Yeah, I need to check. It's more do the same thing, compare with other entries, and yeah.
That's good.
It's very quick.
When will the CMIP7 for industrial emissions be available?
There
are, I mean, read in a format that we can run the model with right now.
Yeah.
Okay.
I mean, it's I mean, I just probably haven't regraded them. Yeah, I probably haven't regraded them all, but they're here.
Yeah, you can discuss later.
We're a bit behind, so
that's here. Yeah. That's not 1750. Yeah.
okay. So next talk will be a remote presentation given by Xin-Yuan Yu, and the title is Attributing 1995 to 2014 Tropospheric Ozone Trends to Specific Sources in the Presence of Climate Variability. So we can see your screen, so go ahead when you're ready.
Okay, can you hear me?
Yes.
Okay, good. Hello everyone, I'm Xinyuan Yu, and I'm a PhD working with Arlene Fiori at MIT. And today I will be talking about attribution of tropospheric ozone trends over 1995 to 2014 in the context of internal climate variability, with a focus on anthropogenic and biomass burning sources. Okay, so what you are seeing here is a figure from Wang et al. 2022 showing tropospheric ozone trends between 1995 to 2017, estimated from aircraft and ozone sound, which are positive in the tropics and the most sites in the northern latitudes, even in regions with mitigation efforts taken to control the sometimes surface ozone, such as the US and Europe. However, observations for tropospheric ozone and especially the free troposphere are very sparse, and the attribution of ozone changes is complicated by large internal climate variability. Thus, we rely on models to interpret the ozone trends. And our prior work used an initial condition ensemble with CSM2 to separate out the impact of internal climate variability and identify the anthropogenic fingerprint pattern of upper tropospheric ozone trends, as shown here. And we searched for this fingerprint in a 17-year OMI MLS satellite dataset starting in 2005. Our finding is that the anthropogenic fingerprint, or we see the human influence, is detectable in the observational record with high statistical confidence after only 13 years of monitoring. And this finding reveals a significant human effect on the ozone trends even in the upper troposphere and indicates promise for us to identify the fingerprints of specific sources of ozone practices, and which is what I will talk about today. So here, to attribute the tropospheric ozone trends, we focus on sources with distinct emission patterns. These sources include the surface emissions of surface anthropogenic and the biomass burning emissions, and the sources in middle to upper troposphere, including the aircraft and lightning NOx emissions. And also, we care about the influence from the stratosphere induced by changes in ozone depleting substances. However, due to the time limit, I will only talk about these three sources today. And take NOx as an example here. I show the evolution of global NOx emissions over 1995 to 2030, and the trend patterns due to these three emission sources over this period. You can see that the trends of different sources are distinct in magnitude and size. So this may leave us some detectable fingerprints on the tropospheric ozone trends. So for this work, we conducted a new set of all but one first initial condition ensembles to attribute the ozone trends from 1995 to 2030. And to save the computational time, we didn't run fully coupled model, but used WACOM-6 with specified SST and CIS cover. And the model has a horizontal resolution about 1 degree and 70 vertical layers. The historical ensemble is generated with historical emissions and forcings following the CMAP6 protocol. And then 3 sensitivity simulations are conducted to quantify the drivers of ozone trends by fixing one forcing agent at 1995 conditions as listed here. And each of them was run from 1995 to 2014. And the 13 ensemble members are created using sea surface temperature and the CIS cover archived from a fully coupled CSM2 historical initial condition ensemble. And therefore, the individual ensemble members are different only in the climate conditions, and they are treated as different realizations. And the ensemble mean is our best estimate of the signal by averaging across the noise resulting from different climate conditions. And I use brackets to denote the ensemble mean and define the signal of each emission sources as the difference between the ensemble mean of HIST and the ensemble mean of the fixed run. Okay, so here comes the results. We focus our analysis on lower troposphere versus upper troposphere, where ozone is most concerned as an air pollutant versus a greenhouse gas. And here shows the global annual mean column ozone anomaly relative to 1995. And the line shows the ensemble mean shadings indicate the ensemble spread. So it's clear that the historical ozone gradually increased in both locations. And that was primarily driven by surface anthropogenic emissions, which are shown in orange. And the blue lines shows the contributions of the aircraft, which is near zero, with a slight positive signal in both altitudes. However, the observed aircraft contributions could be negative, depending on the internal climate variability. And the green line shows the influence of the biomass burning, which shows a negative contribution in most years. This is because of our choice of 1995 as a base year, when the CO and the NOx emissions are higher than later years, except for unusual El Nino event year. And here I want to emphasize that the biomass burning is treated as a first in our simulations with the same emissions applied across all ensemble members instead of responding to the meteorological conditions. Okay, so then what I showed previously is the global mean. So then we now look at the spatially now. So we hope to define the anthropogenic fingerprints of individual sources, thus to provide attribution of ozone changes by comparing the fingerprint of single fusing to that of the hist. So following the approach of many detection and attribution studies, the fingerprint is defined as the leading EOF of the ensemble mean ozone anomalies over this period. And here I show the results for the lower tropospheric ozone first. Here shows the first two EOFs of the ensemble mean historical lower tropospheric ozone, and the explained variants are shown on the top. The same color in the EOF loading indicated regions with ozone varying coherently, and the corresponding principal components are shown on the right. You can see that they represents how strongly these EOFs are expressed at a given time. And therefore, the first EOF of the hist is called the historical fingerprint. We find that it closely resembles the fingerprint of surface anthropogenic signal with a spatial correlation of 0.85, and their principal components are also highly correlated, confirming the consistency of the temporal variations associated with these spatial patterns. And very interestingly, the EOF2 of the hist lower tropospheric ozone mirrors the pattern of the fingerprint of biomass burning. Both show a largest signal in the South America. So these findings indicate that the historical lower tropospheric ozone changes mainly reflect the impact from the surface anthropogenic emissions and biomass burning emissions, with their unique fingerprints clearly emerge in hist. And then we look at the upper troposphere, we find that the similar things. Although the similarity between the second EOF of the hist and the fingerprint of biomass burning only exists in the tropical regions where the biomass burning influence is largest. And I want to mention that the fingerprint of the historical upper tropospheric ozone changes shows a clear increasing trend at virtually all grid points. This reflects the global scale increase of upper tropospheric ozone, and this is consistent with the pattern of the fingerprint of the surface anthropogenic emission signal. Okay. So we further explore the seasonality of the tropospheric ozone trends induced by different fusings. And I show here the contributions of different fusings to seasonal lower tropospheric ozone trends over 1995 to 2014 in June, July, August versus December, January, February. So clearly, except for the South America and the Central Africa, where the lower tropospheric ozone trends are governed by biomass burning, surface anthropogenic emissions basically plays a dominant role in determining the overall spatial patterns of historical ensemble mean ozone trends in both seasons, leading to an increase over the East Asia and a decrease over US and Europe in boreal summer, which follows the pattern of the precursor emissions quite well. While in high NOx regions in winter, the NO emissions titrate ozone. So increases in emissions in East Asia decrease ozone, while decreased emissions of NOx in US and Europe increase ozone. And then for the upper troposphere, we see that the surface anthropogenic emissions contributes to an increase in the upper tropospheric ozone globally across all seasons, with the increase being most pronounced in boreal summer. And the aircraft, which are shown on the bottom, contributes to the increase in ensemble mean upper tropospheric ozone in the northern extratropics, although the signal is very weak. And I do additional averaging along the latitude to see if we can get a signal for aircraft. And as you can see, that aircraft signal clearly contributes to the increase of the ensemble mean ozone north of 30 degrees north. Okay, so we further dig into the reasons of the widespread increase in upper tropospheric ozone in the June, July, August. And I want to mention that earlier work suggests a shift in anthropogenic precursor emissions towards the tropics contributes to the recent increase in free tropospheric ozone. And I show here the trend of NOx and the ozone production rate in upper troposphere associated with surface anthropogenic emissions to further dig into the reason. As you can see that the increase in East Asia is contributed by lifted precursors and enhanced the production of ozone there, although we couldn't rule out of the influence of lifted ozone directly from below the boundary layer. And in contrast, the increase in upper troposphere ozone tropospheric ozone in the Eastern Asia is where the precursor emissions and the in-situ production of ozone has decreased. So this highlights that transport plays a more significant role than the local production in shaping the historical uptropic ozone trends over the US. Okay, so until now, we have focused on the ensemble mean, which is the signal, but can the trend driven by a specific emission forcing be detected in a single realization? Recall that we only have one observational record. So here we use the signal-to-noise ratio to indicate the significance of the signal relative to the climate noise, which is defined as the ratio of ensemble mean trend to the standard deviation of the individual ensemble member trend, as explained here. The signal in regions where the signal-to-noise ratio is larger than 2.18 will be regarded as detectable with high confidence. Okay, so here I recall the seasonal ensemble mean ozone trend in lower versus upper troposphere in different seasons. And I masked the grid points where the signal-to-noise ratio for ozone trend doesn't exceed the 5% significance threshold. We find that the large internal climate variability confounds the detection of the aircraft signal and also the biomass burning signal, except for the south regions in the lower troposphere, which I mentioned that the Central Africa and the South America. But the results indicate that there are promise for us to detect the influence of surface anthropogenic emissions in observational record in these unmasked regions. Okay, so my conclusions for this work is basically over the past 20 years, the surface anthropogenic emissions dominate the ozone trends throughout the troposphere, even in the upper troposphere. And also biomass burning emissions contribute to a decrease in ozone, especially in South America and Central Africa. But away from the south regions, the climate variability confounds the trend detection. And for aircraft emissions, it has increased the uptropic ozone north of 30 degrees north, but the signal is very small relative to internal climate variability. And with these knowledges, we now move forward for the next step, try to focus on the surface anthropogenic emissions, but try to separate out the influence of different ozone precursor species, especially NOx versus CO and non-methane VOCs. And except for the simulations that I mentioned previously, we add more sensitivity simulations by fixing NOx versus CO and non-methane VOCs at 1995 years level to dig into the contributions of different species. And also we especially focus on Asia and fix the different precursor emissions in Asia to further dig into the contributions of them. And feel free to contact me if you are interested in our work. And, okay, thank you.
Are there any questions?
Thanks for a very nice talk. That's a lot of nice work, very comprehensive. I was wondering if it's possible to do source or signal detection with stratospheric contribution.
You mean with our current simulations to do the source attribution of stratospheric ozone?
Yes. If you think it's possible, and if so, I don't know, maybe additional simulation need to be done for that.
Yeah, I think it's very interesting to see how the near surface emissions contributed to ozone in the stratosphere, and
I mean stratospheric contribution to the troposphere.
Oh, okay. Yes, I didn't mention that we actually have 4 more ensemble members where they fix the ODS, ozone depleting substances, at 1950 years level that could be used for this work to understand the influence of ODS. And this is kind of like the influence from the stratosphere. Yeah, but for the general idea, we didn't save out the variables that could quantify the amount of ozone that directly from the stratosphere to troposphere. So
So maybe Tristan, they Tristan.
Thank you.
Okay, yeah, thank you. I don't see because before.
If there's no other questions, thank you again. And we move on to the next talk, which will be given by Pidong Wong. And the title is Fingerprinting the Recovery of Antarctic Ozone.
Allow sharing.
Maybe some here.
Hi everyone. My name is Pei Dong. I'm a graduate student working with Professor Susan Solomon at MIT, and it's my pleasure to be here presenting our recent work fingerprinting the Antarctica ozone recovery. And I would like to first acknowledge all my wonderful collaborators, and Doug and June are also sitting here in the room. This work is currently in press in Nature, and hopefully the paper will be online in the next month or so. But the earlier version of the preprint can be already found on Research Square. The ozone depleting subsidence, the ODS emissions are decreasing since after the 1990s, but it's ozone recovering over the Antarctica. Solomon et al. In 2016 shows that September is a key month to search for the signs of ozone recovery, and both the model simulation and sounding data show consistent ozone increases in September at the lower stratosphere. A recent study using satellite data also mentioned that in September we can see a ozone recovery in the lower stratosphere, but they also noticed that over October we can indeed see a significant ozone decrease, especially in the mid-stratosphere. But this paper have excluded the 2019 southern stratosphere warming, which can partly cause abnormalously high ozone, but they also included the 2020 Australia wildfire and 2022 Hunga Tonga volcanic eruptions. So these can partly explain the abnormalously low ozone. But the point I want to make here is that these multiple evidence are showing that a robust detection and attribution method is needed to quantify the level of confidence in Antarctica ozone recovery. What has been commonly used in Antarctica ozone study is the multiple linear regression. Here I'm showing a most commonly used Lotus MLR method that has been widely used in ozone assessments. The idea of this MLR method is that they synthesize all the available observations to fit source of uncertainties in ozone variability. For example, they fit the source of ozone variability to QBO, to ENSO, to aerosol optical depth, solar cycle, etc. These are very valuable techniques to provide uncertainties on the trends because they only require available observations to do the analysis. But the MLR method assumes that ozone has a linear response to all these predictor variables, and different predictor variables, for example, QBU and ENSO, they are independent from each other. And this is only based on limited observations, so we cannot avoid overfitting. An alternative approach to quantify these sources of variability and uncertainty is to take the advantage of large ensemble simulations with fully coupled ocean atmosphere models with interactive chemistry. So in addition to these large ensemble simulations, we also borrowed the idea of fingerprinting that Xin Yuan also discussed before me, that has been widely used in the climate community to attribute anthropogenic warming. And the idea of fingerprint is that just like human fingerprints, different forcings can have different characteristic signatures in space and time. For example, here I'm showing the latitude versus longitude anthropogenic fingerprints to the surface temperature. And when we increase CO2, we would expect to see more of the warming in the tropical regions and Arctic regions, and less of the warming in the Arctic region, in the Antarctica region. And by comparing this overall pattern in the observation, we can quantify how similar our observation is reflecting this overall pattern. And this level of similarity can indicate that the observation is unlikely driven by internal climate variability. And similarly have also been done for these vertical fingerprints. By our expectation, when we increase CO2, we would expect warming in the troposphere, but cooling in the stratosphere. And the higher we go in the stratosphere, we can expect to see more of a cooling. And indeed, we can see these characteristic signatures of temperature change in satellite observations as well. So the models we used in this study is based on CESM1 WACOM 4. It's fully coupled atmosphere ocean model with interactive chemistry that runs from 1995 to 2024. And there are 10 realizations each for the greenhouse gas plus ODS forcing, the greenhouse gas only forcing, and ODS only forcing. And we also have another 10 realizations of pre-ozone depletion time that runs from 1955 to 1979. And we also compare a suite of 19 different models that participated in CCMI-1. But most of the results I'm showing here today is only based on WACOM simulation. And when we take the ensemble mean, it will give us the first response. And when we subtract the ensemble mean from each realization, we can estimate the impact of climate internal variability. We're comparing the observation from MLS. We use the monthly mean pressure resolved ozone from 2005 to 2023. And the MLS contains the real world force response and the internal climate variability influence. We're interested in 66 south to 82 south. This is the similar latitude being used from MLS, and we use the pressure from 100 millibar to 1 millibar. The model outputs are first vertically interpolated to the MLS pressure coordinates. So what's the fingerprint pattern we're searching for? Earlier, I showed that for the temperature fingerprints, the spatial features of temperature have been commonly sought for. But for these chemical species such as ozone, they can strongly depend on temperature, the solar radiation, and dynamical transport. So here we quantify the fingerprints of ozone as a function of month versus height. And this will help us to separate the different mechanisms due to different forcing. Here I'm showing the ensemble mean of the ozone trend from 2005 to 2018 from the greenhouse gas plus ODS forcing on the left, the greenhouse gas only forcing on the middle, and ODS only forcing on the right. For the upper stratosphere, we see that both the greenhouse gas only forcing and ODS only forcing can lead to ozone recovery up there. In the greenhouse gas only case, because we have a large decrease in the temperature due to increasing CO2, it will slow down the ozone loss rate with Knox cycle. That's why we are seeing an ozone increase in the upper stratosphere. That's just due to greenhouse gas. And in the ODS forcing, we are reducing the reactive chlorine that will reduce the gas phase ozone depletion up there. And in the middle stratosphere, around 10 millibars during June, July, August, this is the polar winter season. And this is the time when we have strong mesospheric descent that will propagate the increasing signal from the upper stratosphere down to the middle stratosphere. And what's unique in the ODS only forcing is that we can also expect to see significant ozone increase in austral spring during September to November. And that's due to less heterogeneous chlorine activation when we decrease ODS emissions. Here I'm showing the MLS observed ozone trend on top and each individual realization from WACOM on the middle. We see that some of the realizations show very remarkable similarity comparing with MLS. For example, this ensemble number 3 here. But in some realizations, we can also see some large decreases in certain seasons. And this indicates that we have to take into account of both the signal and the noise to look at these observed ozone trends to see whether they are significant or not. But before that, I want to first verify whether this WACOM is capable of simulating the realistic observed ozone variability. Here I'm showing the time series of the standard deviation of the ozone time series from MLS as a function of month versus height. We see there is a large internal variability of ozone, especially over October and December in the lower stratosphere. And what's interesting is that here I'm showing the similar standard deviation of ozone from the WACOM historical simulation. That is the time when it's pre-ozone depletion. That is from 1955 to 1970s when we have low greenhouse gas and low ODS. We see that the internal variability of ozone does not capture the observed ozone variability at all. But in climate communities, these internal climate variabilities are commonly estimated from these pre-industrial control simulations. But in terms of looking at these detection and attribution in the chemical world, we cannot capture these internal variability from these pre-industrial control simulations. And here I'm showing the Wacom REF-C2 scenario, which is the high greenhouse gas and high ODS under the present day. And we see that it captures pretty well of this enhanced ozone internal variability over spring. And I'm here also showing a sensitivity test from a fixed ODS scenario when we have high greenhouse gas similar to present day, but low ODS in the pre-ozone depletion time, and it doesn't capture the enhanced ozone variability. And this is suggesting that the enhanced ozone internal variability is mostly due to elevated ODS in present day. And also, because the ozone internal variability, the ozone itself can feedback onto the temperature and general circulation, so it provides a potential pathway for this external forcing to modulate internal climate variability. Here I'm showing the signal over noise for the trend I just showed before. On the left, I'm showing the MLS observed trend over Wacom simulated internal variability noise. On the right, I'm showing the Wacom force response over the Wacom simulated noise. These hatched regions indicate where we have a 95 percentile confidence. Based on these Wacom simulations, what I mentioned earlier, that we're expecting to see significant ozone recovery in the upper stratosphere in all the seasons except winter. And during the polar winter, we're expected to see significant ozone recovery that propagates down to the middle stratosphere. And in Austral spring, we can see significant ozone recovery during August and September. And indeed, we can find these significant ozone increases in MLS as well. So this gives us a very remarkable agreement between observation and the model simulation. And now I'm trying to quantify the level of confidence that we see in terms of the observed pattern. Here I'm calculating the overall signal over the noise ratio. For the signal, I'm projecting the observed trend pattern from MLS to these modeled fingerprints of greenhouse gas plus ODS forcing. So it measures the pattern similarity between these two. On the denominator, I'm calculating the standard deviation of each of these 10 noise patterns that also projected onto the modeled fingerprints. So the signal over noise ratio here tell us the likelihood that the observed pattern similarity can be explained just by internal climate variability noise. And here I'm showing the red lines is the signal over noise ratio from Wacom simulation. And the blue line here, I'm showing the similar thing, but for 19 different CCIMI models. So for the Wacom simulations, it's capturing this internal climate variability, but for the CCIMI ensembles, it captures not only these internal climate variability, but also captures the different model forces to different modeled physics compared to the common external forcing. But both of these ensemble simulations show that after around 2015, we expect to see about a 2 sigma level, indicating that the observed pattern is unlikely due to internal climate variability itself. It has to be forced by these greenhouse gas plus ODS forcing. I'm also showing here in these dashed lines after 2019, because in 2019 we had the sudden stratospheric warming, and in 2020 we had the Australia wildfire, and 2022 the Hunga Tonga volcanic eruptions. And these external forcing are not being incorporated into these model simulations, and that's why we are seeing a decrease in the signal over noise ratio. But if we have long enough record, and also if we include these forcing into the model simulations, we would expect to see an increase of signal over noise ratio. And what I'm doing now is to project these observed pattern onto the ODS only forcing and the greenhouse gas only forcing to see the contribution of each of these factors. The yellow line here is when I project MLS pattern onto the ODS only forcing. The green line here is when I project MLS onto the greenhouse gas only forcing. The higher signal over noise values we see that projects MLS onto the ODS fingerprint tell us that the observed pattern is dominated by the first response to decreasing ODS concentrations. Here are the conclusions. The months and height trend patterns of Antarctica ozone are getting more similar to the fingerprint patterns of greenhouse gas plus ODS in the 10-member CES and Wacom ensembles and in 19 different multimodal CCIMI ensembles. And this pattern of similarity is dominated by ODS forcing, suggesting that the Montreal Protocol in regulating ODS emissions is indeed leading to a significant recovery in Antarctica ozone that is unlikely explained by internal climate variability itself. And these initial condition large ensemble simulations with interactive chemistry provide valuable information to quantitatively estimate the uncertainty in these chemical constituents due to internal climate variability, which may involve nonlinear feedbacks. And finally, the changes in stratosphere ozone variability due to elevated ODS forcing here also highlight a potential pathway for coupled chemistry climate interactions for external forcing to modulate specific modes of climate internal variability, such as the southern annular mode. And with that, I would like to thank you very much for your time, and we'll have to any questions.
Any questions?
Yeah, I have a quick question. So when you say project onto certain model patterns, is it just like a dot product of the two patterns, or correlation pattern, or?
Yeah, I'm just calculating the uncentered covariance between the two patterns.
Oh, okay. All right. Of the whole domain.
Yeah, for the whole domain.
Okay. Thanks.
What would be the minimum number of realizations you would need to find the pattern statistically?
Yeah, that's a good question. I think for these Antarctica regions, maybe we don't need too much of the realizations, but if we're looking for the tropical regions when there is a significant impact from ENSO, maybe we might need to include more ensemble realizations.
Okay, thank you.
No other questions? Thank you again. So I think the last presentation for this session is Hanli Liu, and the title is it's yes for no, transport of nitric oxide in the winter mesosphere and lower atmosphere.
Join, has already joined. Let me see. Okay. Where's the share button? Oh, here.
Well, thanks. I'm going to discuss the nitric oxide in the MLT region. So it's a bit jump in altitude. The reason for this study is really to we have long-term issues with nitric oxide in MLT deficiency, and we'll try to address that, and especially in this case using the high-resolution WACOM-X simulation. So this is an introduction for the previous studies by Randall et al. And you can see that comparison with various observations, the ACE, MIPAS, and SOFI, and they show similar kind of deficiencies in the WACOM simulation. And you can see that this is much lower level in the MLT region than what has been observed, and the same here. And this is in the southern winter hemisphere. It's again very low level of nitric oxide here in the MLT region. And there have been various studies trying to find the reason, the cause, and there are maybe three main groups of thoughts. One is maybe there's some absence of or not considering the D region chemistry that can be a cause of the deficiency. And the other is dynamics. Maybe the eddy diffusion is underestimated in the model. And in this study, they showed the NOx from ACE and WACOM, just normal setup, and then the D region. They introduced Anderson et al. They introduced the D region chemistry, and they found this is the difference between these two. And they found that indeed there are pockets where nitric oxide is really enhanced. But overall, if you look at either this one or this one, compare that with the ACE measurement, in general, the NOx level is still pretty low. By the way, this is time and this is altitude. And this is again the Smith-Johnson study. They did a set of sensitivity study where they tune up or down the Prandtl number, and therefore tune up or down the eddy diffusion, and they showed that indeed there's a very sensitive dependence on the diffusive transport of the NOx. So anyway, you know, these are all kind of I would say this is a more or less a parametric study, and you know, looking at certain factors, how they may affect the nitric oxide. And so it clearly indicates that we have some gaps in our understanding of nitric oxide. And this gap is important because the downward transport of nitric oxide is very important in understanding especially the indirect effects, the IE effects of the precipitation, where in the polar winter, where the NOx in the thermosphere can be transported downward, and it may affect the ozone in the middle atmosphere, and therefore the dynamics in the middle and even lower atmosphere. This is the model we're going to use to look at this problem, and this was presented a year ago. I just want to highlight the experiment, numerical experiment we're going to use or to look at is the high resolution setup and the low resolution setup, 200 kilometer versus 25 kilometer. And it's the same dicore, the SE dicore, and everything else being the same, except in the low resolution model, we have the gravity wave parameterization, which is turned off in the high resolution setup. So this is an analysis approach. Basically, we're looking at the mass flux of nitric oxide due to residual mean circulation and due to eddy mass flux. And in addition, in the coarse resolution simulation, we have this additional term of the parameterized eddy diffusion, which in the Smith-Johnson study, that's the kind of the knob they tune to look at the response of the nitric oxide. So first of all, we look at the model results of the nitric oxide. This is a profile in the polar night, 80° north. In January, this is a mean over January, and the solid lines are the results from the high resolution simulation, and the profiles, the dotted profiles, are that from the 200 kilometer coarse resolution simulation. And this is a log scale. So you can see that it's quite significantly larger in the whole MLT region. And at the peak, the nitric oxide is 8 times 10 to the 7th, which is twice as large as the peak we saw in the coarse resolution simulation. And on the right side is the line contour is just the background or the zonal mean nitric oxide, and the color contour is the difference between the high res and the low res. So again, you can see that in the polar night region, there's a very significant increase in the nitric oxide. So why? What's the cause of that difference? So to look at that, first we look at the vertical wind, the residual mean vertical wind component. This is from the low resolution run, and this is high resolution run. Again, this is a January average. And one thing is that if we look at the MLT region, this is pretty much what we understand so far from the the general circulation pattern in the lower thermosphere region, MLT region, the mesosphere and lower thermosphere region. So basically, your parameterized gravity wave was driving this summer to winter circulation, and then at the winter pole, there will be 2 branches. There's an upward branch, which you can see. This is the green pattern. By the way, this is a nonlinear scale because so that we can see the whole domain. So you see this upward branch, and then a downward branch. And then you drive a return flow, winter to summer return flow. So if you do a mental average of the high resolution, you more or less get a similar pattern. You have this more or less kind of upward flow at places and downward flow at other places. But one key difference is that the spatial structure, the variability is much larger in this case than in the regular or coarse resolution simulation by parameterized gravity waves. And if we look at the magnitude, if we cut through a 100-kilometer altitude and look at the wind, the residual mean wind from the two simulations, the red is from the low resolution here, and the blue is from the high resolution. So you can see that the red is pretty weak and around zero and sometimes even upward. The blue, on the other hand, there are also upward components, but there are very large downward flow channels, mesoscale flow channels. So this is what you see here, the very large spatial variability. And what that does is that it provides a lot of channels for the NOx to come down. And this can be seen from the flux calculation. This is the NO flux, mass flux from the residual mean circulation in the high res and low res. So in the low res, you can see the MLT winter region, it's white here. It's near zero and maybe even upward. On the other hand, if you look at the flux in the high resolution, lots of downward, very large downward fluxes at a lot of places. And this is the eddy term. And the eddy term you can see in the MLT region, it can be comparable to the downward flux by the residual mean circulation. On the other hand, the result eddies from the coarse resolution model is very low. It's kind of expected because it's only the very large scales for, in this case, for the coarse resolution. And then this is the additional term from the KZZ, the parameterized gravity wave. And it does provide a very consistent downward flux. But the magnitude is about order magnitude smaller than what we saw in the high resolution. But you can understand now if you tune this up or down, that will control to some extent the nitric oxide in the MLT region. So if you put all this together and integrate over the polar region, that's what you get. All the blue curves are from the high resolution, and the red are from the regular resolution. And you can see that if you look at the total flux, the downward flux around about 100 kilometers is about a magnitude larger than what we get from the low resolution. So there's a big difference between the two. And but there's another thing we need to pay attention to, which is if you look closely, the nitric oxide is already very large at the top in the thermosphere. And if you look, further up, you can see throughout the thermosphere, the nitric oxide in the high resolution model is already larger. So first of all, we need to understand why. It turns out this is due to the decrease of atomic oxygen in the thermosphere in the high resolution model. So in the high resolution model, because of the resolved gravity wave forcing was modifying the circulation, what happens is that it slows down the downward circulation in the winter hemisphere and enhance the circulation in the summer hemisphere. So basically you introduce a net upward flux, and that will tend to increase the molecular species and decrease the atomic species. So as a result, if we look at the O2-N2 ratio, which is a key factor looking at the composition in the thermosphere, we see that the dotted lines, the regular resolution O2-N2 ratio, this is the latitude, you can see there's a significant decrease in O2 N2 ratio, and which makes the model in much better agreement with observations, the GUVI observation or GUVI observations. And this is another long standing item in our or issue in our model study, is that we always overestimate the O2 N2 ratio in the thermosphere. So what that does is that it changes nitric oxide by changing the quenching of the metastable N, the NCC. This is a mechanism proposed by Zinhuber et al. And because with less O, or first of all, the atomic oxygen quench the metastable N and produce more S, the base state NS, and that's a double whammy for NOx because or NO, because NWD was a source for NO, and the base state N is a sink. So now with the reduction of O, you would expect to see an increase in nitric oxide. And indeed, if you look at the model results, we see comparing the low res, the high res, and the low res, there's a decrease in the atomic oxygen, and also correspondingly a decrease of atomic nitrogen, the base state. And so that's why we are having more NO in the thermosphere. But if we look at the flux, what does it mean for the flux? Does it mean that we'll get more downward transport from the increasing reservoir of NO in the thermosphere? So to look at that, we did another diagnostic study where we used the wind fields and diffusive, the KZZ from the regular resolution model, but used the nitric oxide from the high resolution model, which does have this large NO in the thermosphere. What we found is that in the lower thermosphere, it does show a larger or increase in downward flux, but below about 95 or 100 kilometer, you have the same situation where you have a very small and then transition to upward flux. So that tells us the dynamics was still, even with the increase in nitric oxide, your dynamics is still trying to prevent the nitric oxide to come down. It was providing more like an upward flux. And if you compared with the calculation we did earlier with the high resolution field itself, the difference is pretty clear. So this is really preventing the nitric oxide to come down. But yeah, that's the study. So the summary is that we do get better transport in the of nitric oxide in the MLT region in the winter side and the polar night, and then the parameterized gravity wave was capturing some aspect of it, but it's really not the correct mechanism, by just tuning the KZZ. So what we are doing right now is because this is just a climatological study, we hope that we can take an event, a precipitation event where we see this downward, the long tail downward transport of nitric oxide, and see if the high resolution model was able to would be able to better capture that in the actual case like this one in the let's see that we showed earlier, this kind of very extended downward transport of nitric oxide, and also look at its impact on the ozone chemistry. That's it. Thanks.
So yeah, gravity wave drift can change it, and actually exert the particles, so change the mean flow wind. But gravity wave parameterization also generates the eddy diffusion in the vertical direction.
That's right.
You mean the current gravity wave parameterization generates insufficient eddy diffusion in the vertical direction?
Yeah, that's maybe I just went too quickly. This is try to show that So this is the KZZ from the current parameterization. And you can see that if you look at the magnitude of the nitric oxide fluxes it caused, it's about order of magnitude smaller than what we got here in the high resolution downward transport. And also you can see this is, I think this is a red dashed dot line. That's the KZZ induced downward transport. And you can see that it is pretty small compared to the other, the downward transport from the high res. Yeah.
So in regular WACM, the secondary peak of ozone has always been too small in magnitude. Do you see an increase in the secondary peak in these simulations in ozone with the high resolution, Russ?
Yeah, that's right. I think I looked at ozone, but not I was trying to see if nitric oxide was caused more destruction of the ozone. Now I can't remember which way it goes. It's not a clear difference, but I can look at it again.
Interesting to know that.
So the secondary peak is at like 80 or 90.
Isn't it more like 100? I don't know.
100. Okay.
Not
I'll take a
100,
look.
somewhere around there, I think.
All right. I'll take a look.
Yeah.
I think Rolando.
Yeah, hi, nice talk, Hanley. Really enjoyed that. One thing I wonder about the parameterized eddy diffusion, one thing that is not in this model is any attempt to account for what we might call chemical eddy transport. And the lifetime of NOx goes from about 1 day in the lower thermosphere to about a year at about 60 kilometers. So I wonder whether anybody has thought about including chemical eddy diffusion. This could considerably enhance the effective vertical diffusivity and maybe improve the amount of downward transport through vertical diffusion.
Yeah, no, I haven't looked at this. I was wondering, Rolando, so this in the polar night, at least, nitric oxide is almost like a dynamic tracer, right? It doesn't have a lot of chemical reaction.
Right, but air masses are coming in and out of polar night all the time.
Okay.
So you may need to be able, it might be that it
I agree.
cannot be done in the context of the low resolution model and that you need fully high resolution to do these things. But it may be something that is worth looking at.
Oh, thanks.
All right, thank you.
Thank you. Very nice analysis. Have you chance to look at the atomic oxygen concentration on 110 kilometers differences?
Yeah, I think that's the 110. Yes, I did.
Because residual circulation, what you're talking about, it's major, basically modified due to 25 kilometers at this area. So I
Right.
expect the atomic oxygen empty level to the thermosphere will change dramatically. And this is affecting O/N2 ratio actually.
Yeah.
Transport from the one hemisphere to another hemisphere.
So yes, so you can see it here actually. This is atomic oxygen change. Basically, this is the high res minus low res
I see.
latitude and height for January. So indeed, throughout the thermosphere, there's a decrease.
Yeah, thank you.
Yeah.
Okay, so I think that concludes the session this afternoon. So we'll continue tomorrow morning at 8:30 and still in this room.
Oh, you already have it.